universities for helping you come out here. Without you, this event would straight up not be possible because we can't have a rocket competition without the rockets. You all have put in a lot of work, a lot of money in order to be able to get here. And so this is a PSA and where I'm going to start my little spiel. General guidelines, and I probably should have written this first, is to be respectful of the people around you. There's a lot of people from a lot of places who may think differently from you. There's no politics in this place. You can talk about rockets, but you can't talk about where they should be landing. You can, have your conversations, but be very civil. If you have problems within your team, which you will, because this is a very high stress situation for everybody involved, if you have issues within your team, speak to your team lead or your chaperone, and before speaking to a volunteer. If you have inter-team issues, speak to a volunteer. If you have an issue with a volunteer, speak to me. If you have an issue with me, speak to Peter. Which I don't know what he'll do about it, but we'll figure it out.
I talk to myself enough.
He talks to himself enough. But again, this is kind of, in order to keep things running smoothly, be respectful. If you see something when it comes to safety or any negative interactions, please say something to somebody so that we can address it before it gets too out of hand.
So a lot of you are going to be testing different styles of rockets and fill systems, and you might not be familiar with the team next to you, but if you're doing a pressure test, be sure to talk to the person next to you. If you think that they're doing something unsafe, ask them about it. If you're still unsure, ask a volunteer, and hopefully we can explain it that it's perfectly fine, but if it's not fine, then at least we know.
Yeah, that's also the thing. We have various levels of people here. We have a team launching to 5,000 feet. We have a team launching to 55,000 feet, right? There's different levels here. Ask around. Familiarize yourselves with the people around you. You have a lot of really smart people here. So don't be afraid to go talk to them. You're in a competition with other people, but in a lot of ways, the way we structure this competition, with you giving us your contract altitude, you're in a competition with yourselves and meeting the requirements that you have set. So be respectful for other people and what they have set for themselves, and be respectful of yourselves as well. Generally, at the site, wear your badges and wristbands at all times. We want to know who you are. If you don't have a badge or a wristband at this point, your team lead should have all of them. And please wear them. We really need to control who's going to be out at the site because there's a maximum of 250 people. Generally, follow site and competition safety guidelines at all times. We have a long rules and requirements packet because we expect it to be read. It has a lot of things in it, but if you have ever any questions, that's what we're here for, right? Ask away if you're not familiar with the guideline, but we're going to try to make it as clear for you as possible. Also, drink water, wear sun protection, and look out for wildlife. These are things that we can do, but it's everybody's responsibility out in the desert to be stewards of the environment and stewards of your own corporeal form. So please drink water, wear sunscreen, and don't become a lobster. I don't know if we have any particular questions, comments, or concerns at this point, but we are going to invite our keynote speaker up, who is John Garvey, who is the project manager at Micro-G, and he'll be giving a talk about his own experience through the aerospace industry of a long, storied career over 40-ish years or so. So let everybody welcome John Garvey.
All right, good morning. Thanks to Far Out for inviting me to talk here. I've got a lot of charts. I tend to have a lot of stuff here, and then my niece is going to keep it under control here. So we're going to keep it to 45 minutes, right? I still got 45. Anyway, I think the value what I bring to the table is been in your shoes, done the experimental rocketry. A lot of it's at FAR, and then before that at the Mojave test area right next door, before FAR became available. And part of what I'm doing is showing you maybe some insights of how you take it to the next level. As you'll see, I had big aerospace, if you will, and so when we came in, we tried to use stuff we were seeing. I was at McDonnell Douglas for a long time, and use that to drive what we were doing. So it's kind of a pull situation versus a push, if that makes sense. But anyway, let's see if I can figure the charts out here. Okay, So I'm going to give you a partial history. I'm not claiming to give you a comprehensive of what everybody's done, just some of the stuff we have been involved with. And I say we is a large crowd. Mark Holthouse has been there since the beginning. You'll see photos and you'll see our hair getting grayer and grayer over the years. So I give him credit. There's my bio. Probably what's noteworthy is I'm old enough that I was a youngster when Apollo 11 happened. That imprinted me, so that's when I got the space bug, and after, that's why I ended up out here in California. What's relevant, I worked at what was McDonnell Douglas. It became Boeing. I don't consider myself a Boeing employee, even though I spent 3 years under their banner. That's where I learned the aerospace business. That's before you could go to SpaceX and learn it. If you want to learn rockets, you go to Huntington Beach and McDonnell Douglas's facility. That was one of the primary areas in the world. They built Deltas and other things there. I worked Delta Clipper. I have some stuff on that. If you don't know that, you should know it. And partly what I'm trying to do here is if you don't know the history of the space program, the rockets, you should go back and learn what people did 50, 60 years ago, because there's a lot of things they did or didn't do that are still relevant today. And so Delta Clipper was experimental. That was my first big exposure to Marauder valves. Thank you, guys. After that, we did things with your valves you probably don't want to know about, but they work great in those conditions, maybe beyond the qual limits. And then I got involved with Delta 3, Delta 4, and then I went off and formed my own corporation, Garvey Spacecraft, sold it to what became Vector. I also worked Sea Launch along the way, and then I was at Virgin Orbit, so I spent a lot of time in this building and over in Building 49 and out on Hammerhead. And those are some fun times. And then I've had my own company, Micro G, which is really a little bit of a shell company, but it covers stuff. Stands for microgravity. I can go into that some other time. All right, Delta Clipper. If you don't know that, that was a vertical takeoff, vertical landing prototype built by McDonnell Douglas in Huntington Beach. And a lot of what you see when SpaceX hits a landing, when Blue Origin hits a landing, that traces straight back to that program. That really was the definitive pathfinder. And I say, I like to follow the technology DNA. A lot of what that, I can show you and trace that on charts. I've done that and stuff, where this person went and worked here, that person went and worked there. And my own personal experiences, I was out there and I came back and I started building rockets and started coming out and going to Mark's house and machining stuff and blowing tanks apart and then coming out here to do it. So to me, this is a very critical gateway in the history of rocketry over the last 30 years. All right, so the DNA, I say that you can follow the train. One of them is through what was the Douglas Corporation, and you can even follow this back to when they were building DC-3s and stuff in Santa Monica. Those are the people who developed the Thor intermediate range ballistic missile. That was really critical. To give you perspective, they did that in like 11 months from the time they got the contract to the first launch attempt. That's how fast they moved back in those days. And then that follows up through the Delta rocket. You should know that, although it's been phased out recently. They also built the third stage, the S4 and then S4B for the Saturn moon rocket. Delta 2 is when I started getting on board. I never worked Delta 2, but I sat next to the guys who worked Delta 2, and a lot of those guys then went on to Delta 3 and Delta 4. Like I say, I worked the second phase of Delta Clipper. That was when NASA took over from the SDIO, Space Defense Initiative Organization, and we were doing a lot of new technologies which are now being used routinely. I was then a project manager on Delta 3 and then Delta 4. At that point I left, but I still was working Sea Launch. I was involved in the early days of forming SpaceX. I was working with Elon and his crew. I did not sign up with SpaceX, so I say I was involved in founding it. I was not a founder, take no credit for it, but was involved in those decisions that led to Falcon 1 and guys like Tom Mueller, Chris Thompson, and them going there. And then when at my own company, we started working on nanosat launch vehicle with Eric Besnard, who was a professor at Cal State Long Beach. At Vector, we were building some rockets and got to various levels of success, and finally Launcher 1. So again, that was pretty fun being, I'd be the launch director number 2 over here in Building 49. So that meant I got to get in control when the plane was coming back without the rocket. And people got to go to the parties, and I got to be in control of the return to base. What I'd like to point out for you folks is 58 was an interesting time frame, 1958. I've been very interested in launching small satellites. I was talking to some of you here. I was around when CubeSat started popping up around 2000. I was going to the SmallSat conference in Logan, Utah. So one branch was building bigger and bigger rockets, Delta IV, sea launch for launch and 6-ton ComSats. And meanwhile, Stanford and Cal Poly SLO and Utah State, places like that, are building these small things that you could fit, they were doing secondary payloads. And what I like to point out, once Sputnik was launched, this country had the ability that within a year you had 3 or 4 different launch systems. I actually don't have all the rocket launches back then. But Juno was Explorer 1, if you don't know that. Vanguard, Thor Delta, they put a couple of stages on top of the Thor rocket. Delta, they had Able, Baker, Charlie, Delta, and Scout. And they were launching satellites within like a year or two, which is pretty amazing. So the technology was there. I go back to that because they were doing it in 58 with 1958 technology. So there's a lot to learn. Now, one thing is they had a lot more stages, 3, 4 stages, and they didn't hit the precision, but people were able to do stuff with the technology that is now over 67 years old. Those were some of the early satellites. You should know these. If you don't, Explorer 1 is the first United States satellite. Von Braun's team put it together with the guys from JPL. It discovered the Van Allen belts. So even on the first shot, it was historic. Vanguard, I love it. The first one is this big, okay? It's still up there. It's the oldest human artifact in space, and I like to have fun with people like, how much would that be worth? Jeff Bezos, after getting F1 engines from the bottom of the ocean, or Discovery Channel, they recovered Gus Grissom's capsule. At some point, someone's going to go get that, and the question is when. That's my opinion, anyway. I also mentioned this, Oscar. This was the first amateur satellite built by some folks. They got a ride out of a Delta Thor out of here at Vandenberg. That was done in 1961. That really set the precedent for small satellites. And for a long time, that was the realm of hobbyists. There's a lot of Oscars. And you can follow that path, that DNA, into what became the CubeSat regime. Nowadays, CubeSats don't look like CubeSats. The 3U form factor, the one on the left, but that's from the mission. That should look familiar. That's at FAR, where for NASA, appropriately named our project manager was Big Daddy. You can understand why. And those are 3 Cal Poly students who are real happy because they've got their payload back from a flight we did for them out there. So that's what's possible today. I use Thor Gina B as my reference of a responsive project. So 1961, 62, they would launch out of Vandenberg. These were the early spy satellites. They didn't have good downlink, so they had to use film. And so they had to recover these in capsules off the coast of Hawaii, usually first with the C-119s and then C-130s. They bring them back, and then they bring them back to Washington to what became the NRO. They were launching these 2 or 3 times a week during the Cuban Missile Crisis. So I keep hearing for the last 20 years they talk about responsiveness and everything else. They knew how to do this in 1961. The problem is, a lot of times when we talk about stuff now, people don't like the answer. The way they did it is they had these in storage. They had blue suiters, Air Force people, on reserve 24/7 at Vandenberg, so they could launch them if they had to. When you talk about doing that now, you hear about a responsive launch that they did in 8 months, Victus Hayes or whatever. It's good, but I'm not impressed by it. That's like saying I'm going to get an F-35 off the production line fast and I'm going to get it to the Philippines in 8 months to deal with a threat. It's a different type of thing, but if you need real recall, we had that then. So we've done stuff to model that. So there's a Thor Gina on the left. And that's something we did back in the days of the company I was with, Vector at Vandenberg at Slick 6. The one on the right, that was 3 hours after rolling through the gate at Vandenberg. We were up vertical. We were only using liquid nitrogen, but the fact that we could go vertical, hook up a cryo, and start pumping it through, that was our metric. What can we do? So we focus a lot on the operations as well as just the design. All right, DCXA, that's the second phase. Just so this, but this was a case for NASA and McDonnell Douglas to throw a lot of new technologies on a single vehicle. The one I was particularly involved with, and then they also had history from the S-4B, certain ways to insulate a cryo tank. Again, that's the third stage of the Saturn rocket, and they built those in Huntington Beach. And we built the DCX in the same hangar that we had built the S4B, vertical integration. So we built a composite tank, a liquid hydrogen tank. I say we, I was more a spectator and hands. They let me do stuff. That's what I learned on this project. If a technician is willing to let an engineer do something, you probably don't want to do it. You know, it's like, oh, you want to go inside that tank? You see that tank over here through the opening, and you want to put the insulation foam and put the bunny suit on there? Great, Garv, go ahead. I'd be in there and I'd be saying to the tech, well, what's your job? He's like, well, if you pass out, I got to call somebody to come and get you. You start thinking about that, going, wait a minute, what does he know that I don't know? Anyway, a lot of that. I like this picture because you look on the right-hand side, that's Carl Lemon, the guy with the gray hair. Carl had worked on S4B 30 years before. He knew all about insulation, and he was able to pass that knowledge on to youngsters like me who were clueless, and I can go into that. But projects like this were great for technology transfer and passing on tribal knowledge. So this was the first composite cryogenic tank. It flew at liquid hydrogen, which is actually harder in some sense because that's colder than liquid oxygen. But we didn't fly a LOX tank because people were still worried about compatibility of a graphite tank, carbon, with LOX. So there was an opportunity to fly a liquid oxygen tank, composite tank, and McDonnell Douglas was going to do that on the X-33 program, the follow-on. I went into my boss, I was out at the flight line, Dave Schweickling, and I said, Dave, you know, I know these crazy guys, I've already been to Mojave and met Mark. I said, they're launching rockets out in the desert. Why don't we build some small rockets and test it? Because all our composite tank guys had different ideas on how to do the flanges and all this. And his response was, Garvey, if that's such a good idea, go do it yourself. Meanwhile, get out of here and get my rocket flying, which was the right answer for a program manager. You know, don't let the loose cannon deviate. But I said, I kind of swore slightly under my breath, something along the line of forget you, but close. And I went off and started building rockets while we were out at White Sands. And ultimately, and meanwhile, I was learning a lot of the trade. As I say, they didn't let me dig before you can, work in the trenches, you got to dig the trenches. So this is a good case of me supervising the guys. They wouldn't let me drive the backhoe. I wasn't qualified, even though I wanted to. I will point out, though. Can you guys hear me if I talk loud? Okay, this is easier then. This is more fun. So this guy here, Kenny Burdino, you can't see it, but I point this out because Kenny was a young technician. Again, when I learned, I'll give you advice. Be good with your technicians. They don't make you as an engineer look great or bad. They'll know if there's a tool you need, but if you don't ask them, they can decide whether to give it to you or not. Guys like Kenny were critical to me then and now, okay? When I talk about Murata valves, they know how to repack a Murata valve and make it work, even if you've had it overpressurized, do all that stuff. So they know all the tricks of the trade. So guys like that taught me a lot when I was out there. And once I started building a rocket, so I started building a rocket in the spare time. I'd go over to the salvage yards of Las Cruces and bring back an old 6-inch, solid rocket body motor, and they'd show me how to clean it out and stuff. They would also let me do work. I'm the guy on the right there. They let me stir the paint. That was my skill level. I could stir paint. And sometimes, and a lot of the jobs I got out there were the really ugly jobs, like you got to get in the trench and tighten up the liquid hydrogen lines. When you get down in the trench, you realize you're in the desert. It's already 105 ambient. It's not cooler in the trench, I can tell you that much. All right? But the fact that I stuck it out with them gave me credit with them, so they were willing to work with me. Delta 3, that's me there at the engine bell talking to Kenny Burdino. We were doing testing out at NASA Lewis at Plembrook, and now we're getting to cryo systems. That's my first test. That's the engine I built myself with help from guys like Tom Mueller, who might be a familiar name. So that's the first test, 500 pounds, and now things are starting to get fun. So my goal when I started building a rocket was I was going to get a composite tank and be the first one to fly a composite LOX tank. That would be my little asterisk in the history books, whether anybody knew it or not. And the story I tell is my wife was an aerospace engineer at the time, worked in Space Station, Purdue grad. She came home and she got tired of the garage being full of rocket stuff. Some of you may know that phenomenon. and said, what are we going to do about it? I said, well, how about, I was thinking of calling the rocket Kimbo, because her name's Kim, nickname's Kimbo. And she went in the house, and I said, there's no way that just worked. But it did. And it turned out everybody liked the Kimbo nickname. It wasn't a Greek or Roman god or something like that. The only problem I had is my technicians buddies, well, why can't we name it after my wife? And I'm like, well, Leanne is too long, or if you want to pay the bills, but so our early rockets were all Kimbos, which was this kind of counterculture in the rocket world. So that's why it's Kimbo 1. So that's us out at the MTA. That's a fun team. So that's Mark's head there at the bottom with his sunshade hat in the back, Mike DeVotto, and then that's Tom Mueller on the right. Tom I met when I went to an RRS meeting, and he looked at my pintle injector that I designed and didn't laugh too hard, and he said, let me show you how to do it. And Tom's the type of guy who had a full bed lathe in his garage and was anodizing parts in his bathroom. We said, okay, whatever you say, Tom. This is how I get stuff done. I'm a hack. And so guys, like I mentioned, Kenny Berdino or even a Mark or somebody sees me touching hardware, and their usual response is, Garv, put the tools down, we'll take care of it. Because they know that they'll probably have to undo my work and fix it. And they'd rather have just go away. And so they'll be like, there's somebody over there who wants to talk to you. Why don't you go over there and talk to him, we'll take care of it. So anyway, this is how I get stuff done. I go threaten to do the work and scare them. That's how I was launching Kimbo 2. Then we started getting bigger, Kimbo 3. And then finally, Kimbo 4 is when we flew a composite LOX tank. It is a composite tank on the left. It's wrapped in insulation and aluminum tape. I cut a deal at Microcosm. They were working on composite tanks. They had a small tank that was left over from cycle testing. So they got to say they flew the first composite tank, and we got to say we were the first ones to fly a composite tank. So that's a little bit of like what I'm saying, a pull. I knew from industry that composite tanks, composite structures were the future. McDonnell Douglas needed a $30 or $40 million, contract line item for Marshall to do it. We did it for next to nothing. And that's been our history of doing it. If you know the business, TRL, technology readiness level, our niche was we're going to take stuff to a 6 or a 7. And that's what we were doing here. First time we flew it. All right, on the left is my garage. That's Chris Thompson, who later was, again, one of the first founders or people at SpaceX. He bailed on me along with Tom, Mike DeVotto, another technician again. And then on the right is when I moved into a small shop in Huntington Beach. And this is when Elon came around, checked out what we were doing, and realized, hey, maybe there's something to this. You don't have to be NASA. That's Tom Mueller on the left. And again, if you don't recognize Tom Mueller, he was employee number 1 and was chief rocket engineer designer for SpaceX for years. I heard Impulse might be sponsoring this event. Impulse is Tom's company. So we were working on, that was the original BFR rocket before Elon appropriated that name. Tom had a 12,000-pound motor, and we made a deal. I'll work on the rest of the stuff. You bring the motor, and so it's actually sticking off the back end there. And we were kludging it, but Tom left before we ever got to fly it. But I took those tanks, and they're now out at FAR, and we turned those into static fire test stands for our subsequent 5,000-pound engine. I worked with Cal State Long Beach. Okay, and close ties with them starting about 2002. So next thing we said, well, what else could we do? We said, hey, on X-33 they were going to fly a linear aerospike. They never flew it. If you don't know what an aerospike engine is, go research it up. So I talked to Eric, got some help from Tom, and so it's fuzzy, but that's an aerospike on the right-hand side. The other one has thrust vector control that we're experimenting with. Long story short, we put together a single orifice aerospike, went out, and we flew an aerospike. First liquid propellant aerospike that we know of, because who knows what they did somewhere, in the black world. This is about when the rich guys started coming into the show, changed the dynamics. So Eric and I realized we needed to focus on something before we were doing Brownian motion. We'd do a fun technology, but it wasn't going anywhere. So we said, all right, these CubeSats, these small nanosats, we're going to develop a vehicle that's tailored to launching 20 kilograms to low Earth orbit. So that's in Cal State. We started ramping up. We started getting contract money from the Air Force and NASA. This is a fun example. So we worked with the Air Force, SMC, and they had us do a responsive launch demo at San Nicolas Island off the coast. Pete Worden, the general by then, now various roles, he was like, Elon went to quads, and we got 2 Navy islands 60 miles off the coast. Why do you do that? Can you launch a rocket? I said, sure. So among other things, we flew the Baxter rail out on one of these C-130s from Point Magoo. We launched, came home. Ted Rothhaus drove it out to Point Magoo for us from here. 1 month from the time we got the okay to the time we launched, which I will challenge anybody. That's a joint team with Air Force, Navy, a couple of NASA guys. One of them is Robbie Schindler, who was one of the co-founders subsequently of Planet. And if you look there, Mark's over here. Then Dave McHugh is another FAR member. Rest in peace. So that was a fun project. And we got it in the air. If that rocket looks familiar, it'll look familiar in the future. They told us we couldn't recover our rocket, so we went out, teamed with Long Beach Fire Department, and we started doing water recovery in Alamitos Bay, which again was a fun one and still may be useful in the future. So here's what we're starting to do. There's our first attempt at designing a nanosat launch vehicle, 20 kilograms to a bare minimum orbit, then it became 450. And the problem we always had is people wanted us to keep making more. We want you to go 450, we want 30 kilograms, so it kept getting bigger. We were trying to do a bare minimum rocket, but we put it together. Now we went to Microcosm, I had some DARPA money, and we said, hey, we want 2 of your standard tanks, your Scorpius tanks. So now you got 2 full-scale composite tanks, and we got a 5,000-pound motor that we'd made, and we're moving up. So there we are, launching, but we can only fill it with 10% of the locks because we didn't want to go through the limits. So it's there. There's Eric Bisnard on the left. I like to use this as an example of what's possible. This is the first LOX methane rocket to get off the ground, built at Cal State. Primarily students. So I'll go back. Here's Eric Bisnard. I forget this guy's name. He was working at AFRL. Going back over here. Andrea, she eventually got her PhD from UCLA, spent time at SpaceX, was then at Aerospace Corporation. She's now working at Whitehall, which is something. This guy, Chris Boswick, awesome, one of my key guys, he's at Whitehorse. This guy, John Ford, I call him John Ford because he's the 4th John, I was John 1. And actually he's J4, no one calls him that now except for me. He's running the VAST site over here, so if some of you go on the tours, that's his job. Okay, so he came up through the ranks. This guy's at Millennium. But they designed the engine, and we gave them an opportunity. We said, you design that engine in your design portion, Professor Bisnard, we build it, we'll give you the rocket, we'll give you a chance to be the first oxygen rocket, PRI-6. First time we went out, they blew the chamber off, it wasn't secured, so I said, all right, you have 2 weeks to go again. It was over spring break. We busted it, plugged in spring break, we went out, launched, and got it back. And I actually have that still in my garage, but it's been stripped apart. So that's one thing we learned. If you fly something that someone don't fly it again. We kept them flying our rockets, so that aerospace rocket is gone because we already flew up with the standard engine, punched it, and it's gone. That would have been a nice little historical artifact. So you learn stuff the hard way. But that was a seminal rocket. There it is, launching, made half week. That was pretty fun. Then we got bigger. So we started going towards refurbishable rockets. This was, by now we're up to the P-18, so we went from Kimbo to Prospector and became Cal State. So this is Prospector 18, is D because we ended up flying it 5 times. I say it wasn't usable as refurbishable. We purposely knew that we were going to punch the ferries and sometimes the chambers, but we designed it to be replaceable. It's like a race car, you change the power, the tires. So we ended up, after 3 flights, getting contracts from NASA, and in this case, it's a team of Cal State students and Cal State Long Beach and Cal Poly SLO. And as I said, they had the opportunity to come in and were working on the pad with us. Unlike a secondary or ride share, if you go on a transporting mission, you turn over your payload, it's gone. You don't get to go out on the pad and learn anything. With us, they're out there in the desert with us. There's a launch, we did parachute recovery. I'd be told by guys at DARPA, that doesn't count. I was like, I still got the rocket back. We still got the payloads back, but it didn't count. We then moved to propane. That was our thing, propylene, sorry. We started doing LOX propylene because there's a little bit of performance improvement. The density's better than methane, and that was our technology. And we were using that
the high-rise, the vertical test stand, which is a pain, but Mark was working with us and putting the rocket up there was fun. At that point, we stopped working with Cal State Long Beach. The dean wanted too much from us. He thought we were a real program and started wanting stuff, so we went back to my garage, and there's the team working there. And then we started doing 3D printing, team with Cal State, with UCSD. So they were in charge of building the printer for us. We gave them the rocket launch, and again, getting some experience. 2016, people were starting to get money for rockets, not spacecraft at that point, so you had Rocket Lab and a few others. So I ended up teaming with a guy named Jim Cantrell. He's the guy who introduced me to Elon. That's all I'm going to say about him. Basically, I changed control of my company where I was the boss, but now I had resources to take it up. We had 2 more zeros to my budget. So now we get nice t-shirts, we get nice logos. Business development guys, I keep going back to you guys, but the business development guys are now more important than me. Apparently, I was told that using GSC and Helvetica font blue does not count as a logo, as my executive admin would say. I was like, nope, that's good enough for Garvey spacecraft. So you see, it's a nice thing. But we did get resources, we did go big, and it's frustrating because we were getting close. I had to start wearing coats and ties again. That's in front of DARPA. You can see I'm enjoying my life now doing the business world stuff. It was cool when you look outside your office and you've got a rocket vertical in the driveway. The neighbors were getting excited. They wanted to know if we were going to launch, and I told them I'd be able to launch it once, and then you'd never see me again. We were doing pathfinding up at Kodiak. I think this got repurposed, but we were getting close to going up there, doing engine testing in Mojave. So now we're doing full-scale testing out here at FAR using, I guess that wasn't the Baxter rail, right, Mark? It was the Crisali rail. But we did that. Spaceport, I say, great, let's go. I don't have the video working, but it's a pretty cool shot. And we also found out inadvertently our rocket worked with propane as well. The supplier gave us the wrong gas, and we only figured that out afterwards, but okay. I say that was a $20 million plus launch because we got our B round of funding right after that, so it was pretty serious. And then we were doing testing. I think that was here. I can't be sure if it was in Arizona, but we were doing, you can't see it too well, but static fire testing with our own TEL, transport erector launcher. Now we're going to the real vehicle. That's a composite vehicle, insulated, getting ready for static fire testing, build out a mission control center in Huntington Beach. And we're 1.5 months away from launching when the fire we ran out of bucks. So that vehicle's still sitting there. Love to fly it. So I went and got a real job, Virgin Orbit. That's us over here at Hammerhead. I'm the second from the left. I was good friends with Dan Hart, the guy next to me. He was the CEO. We were both young engineers on Delta 3, 4 and stuff, used to battle. Sir Richard. I actually got to take that photo. That was a cool one. We got in trouble from the safety people because we weren't supposed to be there, but I was with the other LD and I was like behind him, I'm with him. So that was a fun program. So launch that. Then we went back to the garage again. So I stopped building rockets for a little while. How much time I got? Oh, I'm doing good. After reusable rockets, I kind of thought we were like at the point of 1869 when the Continental Railroad was in place, when they drove the spike through at Promontory Point. The rest of us are trying to make faster and bigger ponies. You know, the game's over. So I started getting interested in other stuff, among other things, railroads, just because I see a lot of analogies to what happened in the 1860s, 70s, 80s in this country in terms of enabling commerce. The railroads weren't the key part. It was what was at the end of the railroads that mattered. It was the timber, the livestock, the stuff that was out here that they could ship back east. And that's an analogy, I think, to like a Falcon 9 now. The Falcon 9's nice, but the real money is in Starlink. Right? That's why they can launch 100, because Starlink is the end market. But I'll be honest, I started coming out, I went to FAR Symposium in 2024, started getting the bug, some people said come on out. I went out to FAR out a year ago, went with Cal State again, I started working with them, and I started rethinking it, and I thought, well, they still needed ponies for a lot of other stuff. It wasn't until cars came along 60 years later. So, long story, people talked me into it, and I went to Cal State and said, hey, I've got a couple old rockets sitting on the side of my house. If you want one, I'll help you refurbish it. And it sat there for a few months, things didn't happen, so I brought it back to my house, and I said to the Cal State students, some of them were here, Annalicia's here. I said, if you guys want to work on the rocket, you can come by my garage on Saturday mornings. I'll help you refurbish it. And at that point, I was hooked. Cal State elected not to get involved because of liabilities. So as I say, I had 10 Cal State students working in my garage, but Cal State was not involved, if that makes sense. The kid on the left is actually from Harvard. That's my alma mater. They were trying to get in the rocket business. Finally, I said 40 years too late, so I had him involved. So we had a good team on Saturdays, and that rocket was designed to a very hard design requirement. It had to fit inside my Ford Explorer. I have a 1995 Ford Explorer that we've used for many rocket launches until, and if we're not going to fit in it, then we got to go big. So that was a refurbished rocket. That engine on the back of it's probably older than many of you. It's an ablative Pinto injector, but it still worked. So we came out to the desert. Annalicia is right next to the rocket, so if you see her around and she looks familiar, I can point her out. I mentioned Kenny Berdino. Kenny, 30 years later, I'm still working with him on rockets. Dave Larson, the guy with no hair, another old guy. He was an engineer at DCX. I believe in playing the game for the long term, so that's why I get a lot of people working for 20, 30 years. I mentioned Chris Boswick, these. Chris comes now, but he brings his 6-year-old daughter, and we put her to work. She's drilled holes in there. So, and they flew a GoPro on our last mission. I benefit from that. I don't know. That's good. I encourage you to do those type of relations. There are other companies where they burn you out, and people never want to go back. I won't mention them, but you can imagine who they are. I'm much more a believer in playing the long game. So there we are. That's one of the Cal State students learned to load locks. And here we are. We got a launch off. That was September. Parachute didn't work all the way. I guess that egg timer didn't work on the second deployment. I don't know. But we got enough of the rocket back. I also mentioned several parts of this were built by my high school back in Connecticut. I was fortunate to go to a good high school. They got a 3D printer. They have a CNC milling machine. They have a better setup than I do. All of you have more setup than I do. I'm in my garage now. So they built a thrust plate for us. So I looked and said, well, we can refurbish that, but who wants to do that? Let's go build a big rocket. So it's the same propulsion system, but now we're putting it in here, and it's strategically designed at 24 inches. And the reason for that is you can get wood sheets at Lowe's or Home Depot that are 24 inches. If I make it 25 or 26, which our other rockets were, now I got to go to the bigger size. So strategic requirements. And I found the difference is now I'm having to use really how to use the tools that my techs used to do. So I can almost cut a decent circle on a router, whatever. I'm even getting to the point where I can make two of them the same diameter, which is the hard part. So anyway, we start doing it, and this is a good cross couple. So you've got Dave over here, who's running me, a guy like me. And then I've got Cameron, who recently graduated. He'll be out far out with you guys. And then I got a couple of local high school kids. So that way, the neighbors don't get too bent out. If their kids are involved, I blame them. I said, well, your kid helped build this. That's pissed off. And then Manny here was at Cal State 15 years ago, but he likes doing this, and he hangs out at Far a lot, so he's coming around. And that's Derek Hunkawa. You're going to see him this weekend, so Derek's involved. So it's a very motley crew, but it's a collaboration, and it's united by people who want to work. And that's in my garage. So what I'm doing now is trying to rebuild stuff, but now I don't have access to a machine shop, so we have to redo stuff differently. We're adding Arduinos and long-range technology, which I got pointers by looking at your guys' stuff here a year ago. And so we built it. There's a bigger one. This was at the FAR Symposium in January. Some of you might have gone to that. This is the Foster new rail that he's got out there. They wanted us to put it out there. And it intentionally looks like a rocket we built 20 years ago, Prospector 5. It's because it is. We're following the same technology. So, but now it's the Kimbo 102. So I started renumbering them after Kimbo's 101, 102. About a month ago, April 6th, we were able to take it out again. And there's the team. Mark's probably in some ways, but there we are with the 500-pound, grossly underpowered rocket, admittedly. That's the money shot. And if I was a business development guy, I would stop here, because about another 10 milliseconds later, the aft launch rail guy, which worked fine on the Baxter rail, got caught on the launch rail. So I have a really good video, but I'm not showing it because I'd be embarrassed by it. But I'll show it after we get it to work. But long story short, the range wasn't too good. So we flipped the rocket, landed it, and turns out it was pretty much okay. If we didn't have pride in the skin, we could have probably flown it again after straightening a few things. But we decided to clean it up, so we brought it back, have refurbished it. So there it is sitting in my garage. We're actually working on the next rocket, but now we're making improvements. People don't like wood bulkheads. You know, Fox is trying that. He wants us to change the stuff. So now Derek is helping us by replacing the wood with aluminum. And on top of that, if you're familiar with the LR1 rocket, oh, I lost it. What happened? Well, anyway, I have another picture, but we now are incorporating an LR1 engine in the next airframe. We're hoping to get out in the field. I'm talking to Mark. You guys are all keeping the agenda so booked that it's hard getting time on the flight to fly this. But next steps are we're going to fly the K102 again with some improvements. And then the K103, I don't know what happened there, but the new rocket we want to get up in the air. And then some of the follow-on things. I have some ideas where I want to go long term. I think it's always good to have a long-term goal. I'm not going to say what it is, but I'll just say it's a bigger rocket. Multiple stages. But along the way, you have to do two things at once. You can't put a bigger engine on it and just have a small fuel tank. We've done that. When we Stormy was here many years ago, we flew a rocket like that, and we proceeded to rip the fins off because we took off over thrust to weight ratio of like 8, and the fins didn't like that. So you need to have the tanks and the propellant, so it's kind of, you got to do two things at once. Impedance matching, you used to say. But we're working on it. We want to get back to, again, doing what we were doing 15 years ago, 10 years ago, but doing it more at my level where it's smaller. And I'm always interested in collaboration. I can tell you guys areas I'm interested in, like thrust vector controls, hard, there's a few other things. But hopefully what you've seen is when you start doing your next projects, what you maybe want to do is look at where things are, where the pull is, so that there's interest in what you're doing. And I've had these discussions at universities, and sometimes it's fun to follow a technology thing because it's cool. And that's fine if you know that's what you're doing, but other times if you want to do something that's relevant, get feedback from industry, from NASA, to find out what might be of interest to them, because that's where you might then be able to get the additional support. Fine on the funding. I just wish I was talking to the Polish team. I just wish I had your travel budget. That would be good. I could do a lot of stuff with that alone. But anyway. So that's a long story. That's the history of rocket development out here and what's possible. Hopefully you guys get some pointers. And I guess, do I have time for questions? I think I got like 5 minutes or something. I got 5 minutes. Wow, I did 72 chunks. So I want that always justified. Any questions? Oh yeah, go ahead. It's good if it's still for the model. The real take that you get from the guys who do it for real engines. We're going to Cal State and did it by hand. Again, that's something I just do with everything's targeting. So I got to do everything to teach you how to do that. When we form vector, we have to run that wet machine, some sort of tables and such nice. But the basic technology stuff that's and the reason we like the way it is, a lot of you go to regen and purchase it, and that's all good stuff. We have basically, you have to put one full company, develop it, and optimize it, and then you get it and shut down. You go to it, you turn the wheel up. You play this heavy, we have, let's call it light, but you know what we go to get here, you go to get into a hard surface position, and you shut it off, it shuts off. So, new stuff is the focus. Okay? I go up here around a little bit this morning.
All right. Next is our safety briefing. Fabulous, wonderful. I would like everybody to stick around for this, especially team leads and sub-team leads. That is required for you to stick around for this. Otherwise, you can go back to your tables. But if you would like to stick around for this, please do, because there's a lot to go over. I would also like to find a Peter Tarley that's, again, making his way up. Slowly but surely. Almost there. Oh, it's the hat. Okay, I see. I see. That's special. Okay. Take it away.
I'll have to apologize up front. I don't have any pictures in my briefing charts, but also, like Garv, I've spent a lot of time in the aerospace industry, started in space shuttle and went on to various experimental rocket programs. Also went from being a design engineer to a reliability engineer to being a safety engineer. And I can tell you that the safety engineer is probably one of the better jobs. You may think safety's boring, but we get to look at all the subsystems. We get to evaluate them all so you know what everybody's doing. Subsystem engineers, they only look at their subsystem. So to start with, let's see. So one of the things I'd like to point out is Farsight was developed to handle amateur rockets. And you'll note, if you know what's going on and what you have to do to get to launch rockets, you'll notice that you don't have to get licenses and permits and all that stuff. We did it for you at FAR. And that was my job, filling out all the paperwork to make sure that we could get in there and do things without having you guys to file, do COAs for the FAA and fire permits with the fire department. So I'm also a pyrotechnic operator in California. California is a unique state in the United States because we have pyrotechnic operators that are licensed to do fireworks shows, special effects for the movie industry, and to launch rockets. And so I'm a rockets pyrotechnic operator. We're responsible basically for the rocket teams, any spectators, cars, and aircraft. And we do have a lot of aircraft around, but one neat thing about FAR is that we're in the restricted airspace for Edwards Air Force Base. So we don't get a lot of air traffic of commercial airliners. We do have to go to lower altitudes during the week because the range is open. They have fighter jets flying around. But on the weekends, usually they're not flying, and we can go up to 250,000 feet. So 18,000 during the week, 250,000 on the weekend. Let's see. Also, we're going to have multiple pyrotechnic operators out at Farsight when you guys are out there launching. Since we're responsible for spectators and aircraft and all that, they have the ultimate say. So if they say something's unsafe and you need to fix it, you need to listen to what they're saying. And if you don't, we will throw you off the site. Now, the site limits, you heard Jess talk about having 250 people out there at Farsight. That's because our bunkers that we have 10 bunkers. You can put 25 people in a bunker, and it's concrete overhead, and it also has dirt berms in the front, and there's concrete on the sides. So if your rocket blows up on the ground, we are protecting you. If your rocket goes up, parachute doesn't come out, comes down, hits a bunker, we're protecting you there. We have about 8 inches of concrete on the top, reinforced with rebar, and it's in a steel pan. So if we do have too many people, like if we have over 250 people, we can put them out a safe distance. And that's the difference between FAR and NAR and Tripoli, is NAR and Tripoli use distance. So for really big rockets, maybe you're 1,500 feet away. At FAR, you're 300 feet away because you're in a bunker that will protect you. Actually, two different arrangements for this competition. We have the leak test days and we have the launch salvos. We utilize the viewing bunkers for the safety part of this. The leak tests, we have 6 total times that you can do high pressure decay tests. I've blown up plenty of rockets doing pressure testing, and it does generate big pieces of very sharp metal, and you don't want to get hit by that. During the launch salvos, we have 8 launch salvos where you have a time where you can set up the rocket in the GSE, and then there's the other part where you can recover the rocket and break down your launch setup. So we try to minimize the viewing, the time in the viewing bunkers. And that's a big deal because when we're in the viewing bunkers, you can't do any work. So we set these up so the setup and breakdowns are overlapping so that we could get this all done while it's still light outside.
It's in this pamphlet.
Yeah, if you picked up one of the pamphlets, it shows how the lineup is for both the salvos and for the pressure testing. Let's see what's next. So high pressure leak tests, we have 2 days, Thursday and Friday, where you can do that. There's 3 slots each day for an hour long. So they're at from 9 to 10, 12 to 1, and 3 to 4 p.m. Also, you'll notice that we're trying to do everything during the daytime, so we have to fly between sunrise and sunset. So we try to make sure that it's light outside, so I've done a lot of the work in the dark, and that's no fun because you can't see what you're doing. The launch salvos are Saturday and Sunday. We got 3 slots each day, 1 hour window. You got your 2 hours of setup and breakdown. And let's see what else. Oh, and during the in-between time between the salvos, we give you 2 hours to go out and see if you can recover your rocket. And like I said on the other ones, the setup and the breakdown are overlap. So we can actually squeeze 3 salvos in a day. And then the last day, Friday, we have 2 slots, which are 2 hours each, and there's 1 hour or 2 hours of setup and breakdown, and there's 1 hour for each launch window. So we're going to do something with safety flags. And what these are is visual indications of when you approach the site that says whether there's hazardous operations going on. So if you see green, it means no hazard. If you see yellow, there's something that's going on that you can't be nearby. And if you're at red, you need to be in the bunkers. Or if you're a recovering rocket team and you see red when you're coming back, you don't want to approach the site. You want to stop where you are and watch because we're starting to launch rockets. So we also have pennants, which we're going to use at the individual pads. And the green pennant, like the green flag, says it's safe to approach. Both the rockets and the GSE are safe. When you see a yellow pennant, that means that they're doing low pressure testing, valve commanding. They could be loading liquid propellants. They could be LOX loading. You need to have a person in your group come over and ask permission before a group comes over to see the pad. Let's see, why is this? So the red pennant, it isn't showing, but on that one, we're getting ready to launch. So the rockets are pressurized. There's propellants in it.
Well, all right.
Oh, I'm sorry.
So if you have the red pennant out on your team's guy wires or on the tower or something, what that means is that your critical safety people are the only ones that are going to be there. Do not approach. You're arming your electronics. You're opening your gas bottles. You're about to leave yourself to go to the bunkers. okay, or you're doing a high pressure test. This is kind of your indicator to tell the teams next to you, hey, don't ask for a wrench, okay? Or it's also to tell people that are on your team but are not involved in the last minute operations that they need to be in the bunkers doing what they're supposed to be doing and not just standing around.
Also, we're wanting you to put up a red pennant. When we're in yellow flag, if you put up a red pennant, that means that you're ready to launch. And when all the teams have their red pennant showing, we'll switch the flag to red. And now everybody arms their rocket, and then they leave and go to the bunkers. So it's kind of like this is the local around the pad indication of what's going on and whether things are safe for you to approach or not.
And you need to have one of these pennants on your tower or on guy wires at all times. So you need to indicate whether you're at green, yellow, or red.
Okay, so the major flags. So green flag, it's held at green so that you can do your rockets and GSE setup. And also, if we've just done a red flag, now you're at green flag, allows you to go out and recover your rocket and also remove your GSE. Recovery crews can approach far site from any direction, and all pads should be at green pennant so that people can go over and see them. During this time, rockets can be inserted in the towers or attached to a launch rail. GSE can be set up, but it has to be safe. So that means ignition system off, recovery system off, deployment electronics off, systems pressurized at atmospheric pressure only, or no systems pressurized above atmospheric pressure. And then non-self-pressurizing liquid propellants can be loaded at the time, which means like if you're loading alcohol or kerosene, nothing like propane or liquid natural gas. Also, you can fill your pressurant bottles if you're doing pressure fed on your rocket, but the pressurant bottle has to be a commercial bottle and you have to be using it within its rated pressure, nothing going above it. Because basically, because it's DOT rated, that's meant the bottle is able to be picked up and moved around by hand once pressurized. More on green flag, rocketeers can come and go, prepare their rockets and launch equipment. Spectators can walk up to the pads. You can do low pressure testing like your 150 PSI pneumatic pressures. You make sure you put your flag out or your pennant out saying it's red, yellow pennant, means you're doing testing. And then we change from green flag to yellow when everybody's almost ready. So when we change the flags, we'll sound a klaxon. It's, I don't know exactly how you explain it. It's a loud horn that does like a real loud tone. And that'll happen when we're changing from, let's see here. Oh, this is before. We'll do a klaxon when we change the yellow flag. And then this is before we go to red flag. Returning recovery crews only approach far side on the spectator side, which is on the east side of the property. Non-launching teams should close up your containers. When they launch, they're going to kick up a lot of dirt. So you're going to get dirt into everything if you do not close your containers. And then the pads preparing the launch will go to yellow pennant. And then you can start arming your GSE and rocket. All electronics can be turned on. GSE supply bottles can be opened. We don't want you to fill your pressurant tanks or your propellant tanks yet, though. So you're going to hold off on that, and you're going to do final flight checks.
Unless it's locks.
Oh, unless if it's locks, right. So the teams that are doing locks will have a chance during yellow flag to load their locks. So that yellow flag will be held long enough for them to finish. And I believe we don't have any locks, people, we do? Oh, we do have one team. Okay, so during the yellow flag, you'll be loading your locks, and you'll also have your yellow pennant out. All non-critical badge rocketeers and spectators will move from the pad to the spectator area, which is on the east side. Teams ready to launch will put up the red pennant, and when all pads are showing the red pennant, then we'll transition from yellow flag to red flag. And then you'll get to hear the air raid sirens. So when the air raid siren happens, the red flag goes up. We're now into salvo time when you can launch. So spectators and all non-critical rocketeers will go into the bunkers. All personnel need to leave the tents, the restrooms, the Kwanzaa hut, the cars, and go to the bunkers. And we will have somebody driving around in a quad motorcycle, making sure that you guys are all out of those areas. We will also close the gate so no one can drive up the drive into Farsight. Returning recovery crews do not approach Farsight, like we said before. You'll see the red flag. Critical badged rocketeers will close the LOX manual and remote control vent valves. You'll open your GSC valves, you'll arm your electronics. And then they'll go to, those guys will go to the bunkers along with the FAR staff. When all pads are clear of personnel, all nitrous teams can start filling nitrous. All LOX teams can start pressurizing their rockets. We'll begin launch procedures. So part of launch procedures is all people are in the bunkers, the air and the road are clear. We do have airplanes that do fly around, so we have to make sure they're there. And also now the improvement is the road will be clear because we'll close the gate. We close it remotely. All launches will commence. So LOX teams will launch first, along with the active venting nitrous teams will follow next. When the drogue parachute deploys or 1 minute has passed after the rocket launch, we will launch the next rocket. If a quick fix needs to be done to your rocket, we'll wait till everybody who can launch finishes launching. We'll hold the red flag up. Either one of the FAR out guys or one of the FAR staff will go out with a critical badged rocketeer to see if we can fix the problem with your rocket. And then you either launch it or you don't. When the last rocket is launched and down, meaning it's come down on parachute or it's done a kinetic impact, we'll go to yellow flag. And we'll sound the klaxon. That indicates the salvos are done. Critical badge rocketeers go out to the pads and safe any aborted rockets. So if your rocket is still sitting on the pad, those guys will go out, safe it so it can't launch. You'll drain the LOX, safe the recovery system, safe the GSC. You'll change your red pennant on your pad to green pennant, and then we'll change from yellow flag to green. And the klaxon will sound again. We'll open the road gates, and then all teams are released from the bunkers. Recovery teams can now go out and recover your rocket. If the pad is used by more than one team, that's where we get a little complicated because the team that just launched will have to tear down their stuff, either get the rocket off the rail if it aborted, or they'll have to. What's that? We don't have overlap. We don't have any overlapping, but that's what you'd have to do, is you'd have to have one guy taking stuff down, another one putting it up. And then we start again. So this is going to happen 3 times in Saturday and Sunday and twice on Monday. Now, personal protective equipment. It's really important that you wear a hard hat when you're assembling your tower and erecting it, and erecting your rocket on the rail. And one of the unfortunate things that happened at Spaceport America is a dust devil came through and knocked somebody's launch rail over, and it bounced off their head. So we don't want to have that happen. So safety glasses must be worn when you're doing pressure testing, when the pressure is above atmospheric pressure. If you're doing black powder charges, you should have your safety glasses on. And if you're cutting stuff, you need to have your safety glasses on. If you're doing locks, you should have face shields, cold insulated gloves, and then your outfit should have long sleeves or a smock or a lab coat should be worn. Teams are required to provide adequate PPE for each of their members. And you're going to be graded on this, by the way, as part of your score. There's going to be deductions if you're not wearing the proper PPE. Okay, the other big thing is desert conditions. It's very intense here. We're at 2,000 feet, so the sun is really beating on pretty good. So you should be wearing a hat, you should be wearing sunglasses, you should apply sunscreen to exposed skin. And another pointer that people don't realize is stuff gets hot out here. So if you're going to pick something up and it's dark colored, you should have gloves on. I've burned my hands, and actually silver. Everybody thinks, oh yeah, reflective silver, it should be cool. It's just as hot. I burned my hands picking up silver rockets. Also, we have very extreme temperatures here. So it can be really hot during the middle of the day, and it can be very cold when it's getting near sunset or sunrise. So you should be wearing layers of clothes, and you can add layers when it's cold, take layers off when it gets hot. Also, the sand follows the air temperature, but it's about 20 degrees hotter. So you should be wearing closed-toed shoes, because when it's 120 out, the sand is 140. When it's cold out, like if it's, let's say, 50 degrees out, the soil and sand could be like 40 or 30 degrees. Okay, hot or cold, it doesn't matter. The air here is very dry. You need to drink plenty of water all throughout the day. People will faint from heat prostration, and so you need to keep up with your drinking water. Also, I didn't mention it, but that means also you're going to be going to the restrooms. The nice thing about FAR, because we've been there long enough times, we have flush toilets, we have urinals, so be sure you go and use the restroom, because you don't want to throw a kidney stone. That's very painful. Desert conditions continued here. We have high winds and dust devils, so make sure your launch rails and easy ups are well anchored. Keep storage containers that have propellant handling equipment closed, because dust will get inside there. Make sure tents are well anchored. Keep your sleeping bags and clothes inside the tents. Control your procedures and other documents to prevent them from blowing away. So place garbage in trash bags. I don't want to see trash flying around. Tie trash bags down so they aren't blowing around. Trash and rocket debris. Collect all trash, collect all debris from your rocket. We don't want to leave anything out in the desert. Desert animals. The desert tortoise is a federally protected animal, so do not approach or pick up a live tortoise. It is a federal offense. If your rocket kills a tortoise, leave the tortoise where you found it. Rattlesnakes, do not approach or pick up any snakes you find. Mojave green rattlesnakes are very aggressive and will chase you, so keep your distance. Let the far out staff know immediately if you or someone is bitten. Do not sleep on the dirt. Sleep in a tent or on a cot. Snakes will want to go where it's warm, and that's where your sleeping bag is. We do have scorpions. They hide under wood piles, so I suggest you don't go digging through the wood piles. And the black widow spiders, they like to hide in dark places. And if you go in the viewing trenches, a lot of times you'll see spider webs. You can clear them away. The spiders aren't out until it's dark at night. Rocket recovery. This is a big important one. Take plenty of water with you and search in pairs. We don't want any of you guys to be lost or incapacitated where we can't find you. Try to get the general direction and distance of where the rocket landed before you leave. Returning to the viewing area at far sight, not the pad areas, under yellow flag, and then it says wait for yellow flag if it's red, and if, let's see what I say on the next one. Yeah. If the flag is red, don't come back in until we transition to yellow. Okay, last part. Take your cell phone with you. Write down this phone number for Jess.
Put this phone number in your phone right now.
Yes. So if you guys are having trouble, this is the number to call. If you're lost, you've had a breakdown of your vehicle,
Been bitten by a snake.
or bit by a snake, that's even really important. Okay, I'll show this phone number at the end, so. Call for help. The vehicle gets stuck in the sand, you become lost, you run out of water, you get injured, you get bit by a rattlesnake. Please note where your location is, and if you can't tell where the location is, a lot of people have GPS on their phone. You can give us the GPS coordinates, call the far out staff and report your location and your condition, and we'll come and get you. If you find a rocket and it isn't from your team, do not touch the rocket. Rocket pieces or recovery parachutes. It may have uninitiated recovery deployment charges. Note its location, take a picture of the rocket. You can text the picture and location to far out staff, which is that other phone number I showed you. If you find your rocket, do not touch the rocket pieces or recovery parachutes unless you are trained to safe your rocket. That's really important. And if you're going to touch stuff, wear gloves when handling your rocket. It's probably going to be very hot because of the sun. And also, if it's done a shovel recovery, it'll have sharp edges and broken metal, fiberglass, and carbon pieces. Also, if your rocket is heavy, make sure you bring multiple people out with you so you can lift and carry the rocket, and you should limit it to 40 pounds a person. So if you have a 120-pound rocket, 3 people should be picking it up. Unfortunately, I had this experience with it. It took 6 people to carry back one of our rockets, and even 40 pounds is pretty heavy. If your rocket has impacted, recover all the pieces of your rocket. We don't want anything left out in the desert. You should bring trash bags with you and bring a shovel and gloves. Okay, conclusion. We want you to be safe. We want you to enjoy yourself while you're doing this. You need to obey the pyrotechnic operator if he tells you to do something, like get in the bunkers, get in the bunkers. And again, recovery team, contact Jess if you have trouble. And there's her phone number. And like I said, have fun. This is a lot of fun. I've been doing this for 40 years. So, want to add anything?
So the other thing we have is, could you actually grab the whiteboard there? The little whiteboard there? So Mark is going to grab our little Salvo whiteboard. Team leads are going to be given a tag that has contact information of, who we reach out to. And they're going to place this little magnetic tag based off their fill time on the y-axis and which salvo they intend to fly in. So it helps keep track of your rockets, and we know who's flying. But also, if you need to vote to not have a launch and no one really wants it, that will let us know if we just want to cancel the whole yellow flag, red flag thing and let you work through it. So if I have 5 teams wanting to work through a salvo and 1 team that's ready to launch, I can move them back 1 in the day, and we can maximize the number of rockets that are going to actually fly that day, and that's our goal here. we'll discuss this more when we're doing setup, but I just want you to be aware of it. Yes, do you have a question? The static firing teams will mark when they want to do their salvos, but they will not have the vote value that the launching teams do, because you can do it any day we're out there. Okay? These rules are all in the rule book under salvo voting conditions. So, you know, little control find works very well. I know it's a long document. It was awful editing it and writing it. I can only imagine what it's like reading it. The flag stuff is also in there, and rules on how many people can go out at a time. We also don't want 100 people wandering through the desert. So there's a maximum and a minimum number of people that you want to take out for your rocket. Are there any other questions? I'm the one wearing the Hawaiian shirt, so I'm pretty easy to spot if you do have questions, and I'm here all day. So, oh, hang on.
So for drones, yes, you can use them to record your rocket launch and your setup. Our rules are you do not fly drones over people or into a crowd. They need to land away from, be launched and land away from people, probably about 20 feet or so. If you violate that, your drone will be confiscated.
Another thing on drones, assume that at the top of each rail, there's a 45-degree cone. Do not enter that cone. We do not want you intercepting drones. While that might get you a job at Raytheon, we don't want you to have that achievement here. So if you're not launching, you're going to remain at green flag. That tells us there's no hazard at the base. And we know where the teams are. So because of that, that chart, with the tags, we know who's going to be in a salvo. So we look at those towers and we look to make sure they're ready to go. And we make sure that there's not some hazard that's present at another team's pad that's not launching. The one thing is, if you're not launching, make sure that everyone's cleared out and things are safed by yellow flag. And we do not want to have to chase you down. There's a long list of deductions for various safety infractions or delaying other teams. Basically, anything that you could think of doing that would be not a good idea to do, we have a point deduction for it. So if you're delaying red flag or yellow flag through operations and that you're not like actually trying to launch, then there's a deduction based off how long you delay other teams. So the sooner you get into the spectator area when you're not launching, the sooner that you're in the bunkers when it's time to get in the bunkers, you'll be fine. You dilly-dally and it becomes a problem, there'll be deductions.
Anybody else?
Okay.
The tours.
Yes, so we think we have our tours coming up. 10:15, I think it starts. Oh, we're right on schedule, yeah. So tour block 1 will be starting off, and yeah. Yeah. So are we doing a recovery briefing here, or are we doing?
I assume we are.
She's on the phone. Okay, so for the recovery teams, if you could stay, and the rest of the people can go to booths or your tours.
All right, for people who are going on tours, there's a VAST tour and an Impulse tour that you should have pre-signed up for. And I'm going to ask that the VAST and Impulse people coordinate that. I think there's a couple already here, but they're right behind the banner. I also wanted to say that for folks who are signed up for the VAST tour this afternoon, we got word like this morning that they're running ops today and they won't be able to do it, which kind of sucks. We'll see if there's something that we could do before afternoon for those folks, but yeah. I'm going to go over some general like recovery briefing things for folks who are leading recovery, and I'll do that. I'll try to get that out pretty quickly. There's not too much to talk about there, and then you're free to walk around the booths. But otherwise, yeah. So stick around if you're doing recovery. Otherwise, please chat with teams, chat with sponsors, buy some merch maybe, that kind of stuff. Recovery folks. Okay, let's have a little chat. Okay, wonderful. This is working great. This also might die soon. Okay. So some of this was we already went over it, but I'm going to reiterate it in its own thing as well. I just didn't realize that some of this was already going over. So we're talking about recovery. Again, this is all in the briefing, and also like all in the rules. This is only go out for recovery after checking your full recovery team in at the recovery table. Everybody who's going out for recovery will get a little sticker on their badge so that we know that you are going out for recovery. The maximum number of people recovering is 2 plus 1 person per 20 pounds of dry mass. This is so that you can switch off so that, you're not, carrying 20 pounds the entire time. But also this is because we cannot have too many people out on the range, and we need to be able to control who's out there. All portions of the rocket must be retrieved in order to be able to properly score it. If there's a piece of your rocket missing, we will be weighing all of the pieces of the rocket, so we will know. Generally, each team will be given 2 FAR radios. We have radios that are programmed and have the recovery frequency on them. I'll talk about that in a little bit, but failure to return these will result in a fine equal to probably the amount of that radio, but just please don't lose them, and I'll be very angry and very mad. Please remember desert safety, wear appropriate closed-toed shoes, a floppy hat, and drink water at least every 10 minutes. Bring a lot of water for everybody because it will be probably 3 times as much as you think that you should be packing. Having just one person, like, I know that Columbia has like the most, for example, Columbia has one of the most wonderful setups, which is like the camelback. Are you guys still doing the camelback things? Beautiful setup of just having a backpack that they can drink out of the entire time. Very useful for recovery, allows you to still, be able to carry things without having to, worry about your hands being, like, busy. So consider that when you're walking out.
push the power button, you get a red light, which means it is.
No, it's battery, normal battery.
Yeah,
Oh, so Jeff must have this battery.
he's got replacement batteries.
Nice. So that's nice.
And it's actually, it's the power button. Light, yes.
Hello. For everybody here, there was an accident at one of the test pads, not for one of the companies that we're touring, but one of the other ones. And so the operations at Mojave Air and Spaceport are kind of swamped right now, and tours are delayed. I repeat, tours are delayed. So if some of your team members have started leaving, they cannot because something blew up. So classic to have that happen today. My apologies. So for folks who are going on the Impulse Tour, they're back open. So you should be free to go on that tour whenever. And I do believe that you should drive out to the site yourselves. Thanks.
Actually, the first thing I decided on. I was taking a walk at the beach like last June and came up with all of this and decided to build everything sort of around the things I wanted here. So I guess I should explain sort of the differences in the rows here. The way the system works, it has a fixed amount of memory that the fill and fire mode share, so it switches between different sample rates when it goes from fill mode to fire mode to conserve that. The rows on the bottom, though, the installed capability is what I've actually built into the box. The maximum thing is a combination of what it's designed for and what I've actually tested it to. You can see at the top there's a little graph of actual test fire we did with it with Big Liquid. It's working very well now. We've done 12 test fires, I think, with it so far. 4 liquids and the rest hybrids. But yeah, let's go next. Cool. This was a pain. So Alex and I last summer decided it would be a wonderful idea to machine the entire enclosure, which resulted in a very pretty box, but a lot of design and, on his part, manufacturing work. You can see here, so in the upper right, that's the box without any of the things installed on it. I think I showed some of you that earlier, but the bottom bit doesn't have any boards mount to it at all. Just the top bit does, and that sits down in there. The advantage of it being machined is that it's very well shielded and grounded and ingress protected and everything. It just took a very long time to make. But there will be more pictures later, but you can see in the middle one, the 3 little modules, one of them is covered by a little plastic bit, are the acquisition assemblies. Those have the boards, I guess you can see them in the lower right. They stack together. Pictures of that later. But then those communicate with the thing on the, I guess, left of that, which is the sort of main controller and sequencer thing of it. Cool. So you see the little arrows, my little very nice arrows. So there's 4 channels to a bank. All the 4 channels go onto one acquisition board, which plugs into one, Each 4 channels go into an analog front-end board, and that plugs into an acquisition board that has all the digital stuff on it. The communication between all of these is just over UART. The analog one, of course, doesn't have any, but this little combined motherboard thing does. The reason it's combined is because the first revision of this didn't work very well, where I had, instead of having the triggers on the board with the little sequencing microcontroller, I had a separate board with the little trigger chips that plugged into that. And it didn't work, so when I redid it, I combined the 2 to save a little money, because time was getting tight at that point. And yeah, I'll talk about the communication to the laptop a bit later, but this is just the internal stuff. Cool. Okay, this was the fun part. This is the fun part, also one of the first things I came up with, and also kind of the important part that gives it a very low noise performance. You can see in the top part, this was a mistake when I was testing it. I had forgotten to put a scale factor in somewhere in one of the filters, and so the data was actually scaled by a factor of 64, but it was quiet enough that you could measure like a binder clip or a pen on it, which I was very pleased with. But yeah, so you can kind of see how it works here. So the sensor and the excitation voltage count as part of the signal chain, because if the excitation voltage is drifty, that will also cause drift in most types of sensors. But the cool bit is after that, I just use commercial instrumentation amp. That's on the next slide. There's filter, sample and hold, pretty traditional data acquisition system, except this digital part here. It's what's called a multi-rate system, where you use digital filtering and downsampling and software to be able to select different sample rates. You could also get extra resolution out of that, but I did not in this case. Yeah. Very pretty board. This is the first board I designed for it. This is the analog front-end board. These are the 3 things you see on the front of it where they have the connectors sticking out. This thing bolts to the chassis by those connectors. And yeah, so each of those shares a common sampling clock with the sequencing microcontroller at 2 kilohertz. So it's always just running, taking samples 2,000 times a second. This thing has no control over what's going on. This is all hardware. The microcontroller downsamples that later and filters it and stores it and everything. It's actually upside down in this picture. The screws are supposed to go the other way, but it also screws into the chassis by those 8 screws you see around the outside. Cool. Amplifiers relied very heavily on commercial op amps because in 2025, commercial op amps are very good. The APA 2202 has all these built-in overcurrent and overtemperature protections and things, but it's also quiet enough to use for important analog stuff like the I've used the force amplifier and then the sample and hold amplifier below there. I also used it for the filters, which are on the next slide. But yeah, so I spent actually quite a lot of time at the beginning choosing which op amps I wanted to use, which I'm glad I took the time to do that. It ended up being very important to the overall thing working well. But then I also used the INA 823 for the sense amplifier, and I was able to get a cool reuse of a part out of that because I also used it for, there's an option to excite sensors with current instead of voltage, because like resistance temperature devices need a current instead of a voltage. And so I used this also for current sensing in that circuit. And then sample and hold, I decided to just build the sample and hold with a little switch and a capacitor instead of using like a commercial sample and hold chip. Just because this was smaller and I was already going to need to get very nice capacitors to use for the filter. But yeah, I don't know how well it resolves, but you can kind of see the schematic there. Cool. Analog anti-aliasing filter. Another, probably, maybe the most important thing on the analog front-end board. Yeah, aliasing bad. Aliasing particularly bad for rocketry because combustion instabilities can very easily cause like huge signals at hundreds or thousands of hertz on top of your normal thrust or pressure measurement or something. And so particularly in fire mode, it's very important to have very, very good anti-aliasing performance on the thing. And so even though the like theoretical max or minimum sample rate you would need if you had a hard 100 hertz cutoff on your signal would be only 200 times a second, I actually sample it at 2,000 samples per second and have a 100 hertz filter before that, which gives very, very good anti-aliasing performance. And there'll be more on that later with digital filters. This was an important thing to get the design right for, though. I went with a type of capacitor, which is kind of cool. They're polyphenylene sulfide, I think. Very good dielectric material for a capacitor. They're very linear, and they absorb very little charge and hold very little charge into the next time you turn it on, which reduces like offsets in the signal. But Panasonic makes these nice little surface mount ones I use, so that was cool. Okay, configuration. The way I did it, none of the gains and stuff are software configurable. I thought about doing that, but that would have been expensive. So the way I did it the old school way. The backs of all the analog front ends, the parts that's still accessible, even when it's installed, has all these resistors and capacitors on it that you can just swap out different values of to change the gain of the amplifiers or the bandwidth of the filter, or switch it from current to voltage excitation. So yeah, I don't know how well you can see, but there's like a missing chip footprint there and a missing resistor footprint there, and different things could be installed to get it to have different sensors that it can connect to. Right now we've just got it installed for 10 pressure transducers and 2 load cells, but theoretically it could be any combination of resistance temperature devices, pressure transducers, and load cells. Digital bit, I think this is a very pretty picture. This is the acquisition board that plugs on to the analog front end board. This bit has the multiplexer between all the channels. It has the ADC, it has the voltage reference amplifiers, and it also has all the stuff you see here. The system has 4 microcontrollers overall, which ended up being very complicated to get them all to interface with each other over UART, but did work in the end. But these 3 modules are all identical, and they have one ATmega 1281 running at 8 megahertz, which is slow, but still works because of something I'll show later. But yeah, and there's these nice little machine shields between each of them, which keeps them very quiet when they run. Cool. Digital filters are wonderful. Digital filters are the secret. You should use digital filters if you're not. We didn't last year when Jackson and I built a very sketchy data acquisition system, and it was very noisy. So I did include them this year, and the noise performance is way better. The types of filters I ended up going for were a Gaussian filter and a moving average filter. You can see in the little drawing on the lower left, there on the left, if you've not heard of that before, that's the impulse response of the filter. This is sort of a function that you apply as a weighting function for a moving average on your signal. And what it does to the frequency components of the signal is it effectively multiplies them by the other plot you see on the right, which is the Fourier transform. Technically, this is the Fourier cosine transform, but in this case, same thing of the signal. And if you look at the simple moving average, which is just a flat function that you weight the signal by, it has this horrible sync function thing that's called in frequency. And so even though it will cut off frequencies right near its cutoff frequency very well, it will peak later again. And so it's not a very good anti-aliasing filter because frequencies up in those higher lobes can still get through into the thing. But the Gaussian is very good because it rolls off and never goes back up as you go higher in frequency. However, the Gaussian is way, way, way more expensive to compute on a microprocessor than the simple moving average. So the way I did it is I have the Gaussian always running to take 2,000 samples a second down to 200, and I have, which is for fire mode where aliasing is a big problem. And I have a moving average to take it down to 20 samples a second for fill mode when aliasing is not a big deal. Convolution. If you've not seen this before, this is how you apply those filters to a signal. You convolve the signal with the impulse response, which is sort of like applying that weighting function as a moving average backwards instead of forwards. But because my impulse responses are symmetric, it doesn't matter technically which way it goes, and you can just apply it forwards normally. Yeah, so right down here, this is the actual filter kernel I used for the Gaussian function. These are all the coefficients that weight the different sample points. So this bit in the middle that's up in like the 2000s, that's the sample that it's actually recording, and all the other ones are the coefficients of the ones near it that get included in the weighted average. Yeah, let's see. So normally convolution would be way too expensive to use for something like this. I have an 8-bit, 8 megahertz microcontroller, which is not very fast at all. And I actually told some people I was interviewing with last year about this, and they said, nah, how are you going to get that to work on an 8 megahertz microcontroller? This is how you do it. If the whole point of the filter is that I'm going to reduce the sample rate from 2,000 to 200 or maybe 20 anyway, so you don't actually need to compute the value of the filtered function at all of the sample points in between those ones you're going to save. So what you can do is sort of what you see here. You don't need to apply that Gaussian at all the points in between. You only need to apply it at the ones you're going to save. The other thing you can do is you can scale the coefficients in your filter kernel so that they add up to a power of 2. And then instead of having to use division, which is horribly slow, you can just bit shift everything down in the end. This is why I had accidentally got a gain of 64 on the signal instead of 1 like it was supposed to be one time, because I had forgotten to bit shift it back at the end. But this is a cool way that something I've thought about that maybe do in the future would be to actually get it to say floating point data, because you could get it to check when it exceeds some certain threshold and then change the amount it bit shifts back by. But yeah, so these, if you wanted to, which you probably don't want to, but you could add these all up and see that it would reach this particular power of 2, 65,536. Next thing, actually last thing I think, interfacing. So a lot of people were asking how it communicates with a laptop, and what you see on the lower left is exactly how it does communicate with a laptop. It is VS Code's serial monitor. It is nothing complicated at all. It plugs into this little thing I have circled, which is a like USB-C to A adapter with a USB-A to XB holder adapter thing, all covered in tape. And so yeah, you can just send it commands in the serial monitor, and it will listen to those and tell you what you've got. So this first one here is pulp, that's pole pressure. We use that during fill, and it'll return a number for you in this very special unit I came up with, DSI, decipounds per square inch. Because I was working on the data export function and it was terribly slow. It still is terribly slow, but I needed to drop some characters to get it to export faster. So what I did is I dropped the decimal point. It was ordinarily 4 digits, decimal point 0 PSI. I just dropped the decimal point and made it DSI, and so it's much faster to export. So silly unit, but good reason for it. Next thing here, this is actually a pretty representative sequence of how we normally do test fires. We open valve, well, we tare it first. We check what the unfilled pressure is, unfilled mass is with pole pressure and pole mass. We start recording, have to remember to do that. Then we hit nitrous toggle, nitrous on, self-explanatory. And then we just keep checking with pole pressure and pole mass every few seconds to see what it's got up to. And once it's at our target, mouse off, fire, stop. And the way it works is when you start recording, it starts recording at 20 samples per second, which is intended for fill mode. But when you type fire, it switches over into fire mode at 200 samples per second. And there's nothing complicated at all about how it makes that transition. It just has this rolling list of numbers in memory that it's always computing both of the values for both of the filters, and so it just switches between which one gets recorded whenever you give it a fire command or a stop command or something. But the way it protects the memory is I used a cool kind of memory called, I think, magnetoresistive random access memory, which is non-volatile. It's kind of expensive, but it's non-volatile and it's cool and easy to interface with. And so what I do is the highest address here, the reason there's 65,535 instead of 36 total lines you can store in the thing is because the highest memory address is reserved for the fire pointer, which records at what point in the memory the data switches from being fill data to being fire data. And so when you go and export it later, the thing will give you a different time step when it's above versus below that number. And then also, if you turn it off and then back on again, the first thing it does is it checks if that fire pointer is written to. And if it's 0, it won't let you record any, sorry, if it is 0, it will let you record something because that means a fire hasn't happened before. But if it's not 0, it will not let you record anything because that means that a fire did occur previously and you still need to get data off of it. You can see in the lower right there, other interfacing options. I made a very nice keypad for this thing. There's been, I think Isaac and I and some others have had a slight obsession with a TPU lately. So I decided to print many things out of TPU for this, including gaskets and this keypad. So I think it's kind of hard to see here, but there's a bunch of buttons on that keypad you can press to almost run a test fire without the laptop if you wanted to, which you don't really want to, but it's nice for shop testing and things. Yeah, I think that's about it. Yeah, cool. The end. All right. Questions? All right, cool. Bye-bye.
Hey everyone, my name is Adam. So you may recognize me because we did a similar presentation last year. So this is somewhat of a continuation of that. So we're continuing our valve component development, this time for locks. So I'm going to be talking high level about some of the developments we did, and then Theo is going to be talking specifically about the run valve, which is our largest valve to date, and went through an extremely strenuous iteration and development process that eventually got to a working final product. So, yeah, Theo, introduce yourself.
Hi, I'm Theo. Yeah, I joined the team this year. The run valve has been my main project throughout the year. So, yeah, excited to present.
Okay, so quick overview of our system. So it's a regulated pressure lock system. It's over in the back there if you want to check it out. But we require 3 cryogenic oxygen valves. So that's based on the wonderful rules from Mr. Peter, and mainly informed by safety, functionality, and having safe abort modes. So all of the valves are really trying to balance oxygen safety, cryogenic reliability, and then manufacturability, minimizing overall mass, minimizing cost, and finally being designed for assembly, roughly in that order. So we'll dive in a little bit on the high level of each valve. So this is our PNID. It's quite large and a little scary. So kind of zooming in on the main parts. So a run valve here, this connects directly to the injector, and that provides locks to the combustion chamber when we are ready to static fire or launch. We also have our fill valve. So the fill valve is a normally open valve that is closed when pressurized. The reason it was designed that way is so that when we detank our nitrogen system, it will also vent our fill valve, and it will open and start draining out the side of the vehicle when we have the umbilical disconnected, so at red flag. And then we also have the vent valve here. So the vent valve is basically for constantly purging our ullage to make sure that our tank pressure is at ambient. So if we didn't have that valve in place, as the locks boiled off, we'd slowly build up pressure until it went supercritical, which would be a good day for our burst disc, but a bad day for the team. So quick overview of the component requirements. We needed it to be compatible with locks, and then also liquid nitrogen, since that's what we used all our cryo testing for. And then finally water, which by virtue of being compatible with those two, it also is compatible with water, but it's important to make sure that there wouldn't be any adverse corrosion. Because we did hydrostatic testing for proof pressure. So the MEOP is 700 psi on all of the valves, and we did proof testing to 1350 or to 1050 on all of the valves. And we also have a design pilot pressure of 250 on the run valve and the fill drain valve, and that's based on kind of earlier specs. And we revised that to 700 to consolidate down to a single low pressure string with our pilot regulator. And then they have kind of different requirements for sealing. So when we're doing our testing, we try to keep in mind when we accepted a certain amount of leakage. So the run valve has to seal for about an hour because it's sealing through the entire cryofill and then our entire nitrogen fill. So that has the most stringent sealing requirements. The fill drain valve has to seal for about 30 minutes. So after we disconnect the umbilical and then we start filling with nitrogen. And the GOX vent valve has to seal for about 30 seconds. So that's really fast. It's just when we pressurize the tank that has to close. But it has to close quickly. So you can see the actuation speed. That's mainly driven by a combination of our performance. So the faster the valve actuates, the faster we get thrust, and the faster we're going off the rail, so the safer our rocket is. And then I'll also talk about the hysteresis with the GOX vent valve and what drove that requirement. So we have some components experience, mainly with a coaxial pneumatic valve for nitrous. So that was 6061 aluminum. And previously with a pyro valve that I think at this point predates everybody on the team. And that was a pyrotechnic valve that we built also for nitrous. And so we have about 1 year of experience with pneumatics, but we had no experience with large stainless steel parts, no experience with cryogenics, and no experience with oxygen, either in a liquid or gas state. So a lot of learning that we had to do to kind of get to the finish line with these components. And it was really a joy to lead the team and learning about that and developing that. So the first step was we had to qualify the static seals. So these were PTFE O-rings that were face seals. So you can kind of see a cross-section here of the two different types of O-ring seals that we tested. The PTFE face seals passed. So when we torqued those down to spec with high compression percentages, so about 35 to 40% compression on those O-rings, they would permanently deform and form a seal even at cryogenic temperatures. But the kind of downside of that is they weren't reusable. So each time we uninstalled and reinstalled a component, we'd have to replace those O-rings. In this case, we accepted it because the alternative would be like a spring-loaded seal, which was like an order of magnitude more money. So this qualification campaign, in addition to testing welds for our tank, also saved us like over $1,500 in spring-loaded seals. And we did hydrostatic testing up until the tank burst point of 1925 psi. Then we also bought some commercial off-the-shelf dynamic reciprocating seals. So these are pretty standard for cryogenic operation and even just for like valves in general. So we bought V-spring spring-loaded seals. The way these work is you have like a plastic that has a much higher thermal contraction coefficient compared to, like, for example, the steel or aluminum it's sealing between. So in this case, we're doing steel on steel seals, but as we thermally contract, if we use, for example, an O-ring, not only would it lose its elastomeric properties at cryogenic temperatures, but the material would shrink a lot more quickly. So to prevent that, these have a very clever design where they use kind of a V-spring to push outwards, and so as it shrinks, the V-spring pushes outward and maintains a strong seal. So for example, they were only unidirectional, so they didn't seal in two directions well, and that gave us some trouble. And they also required a two-piece design, so you couldn't just have like an internal or external groove. You need to have two pieces that then had like additional fasteners, and that added more complexity to the assembly, but also created some interesting opportunities for mass savings. So why even do custom valves in the first place, other than being cool? So especially for LOX and cryogenics, solenoid valves are very expensive, and they're very hard to procure. So it's very hard to find anybody who won't do it without like quoting you a very large number with a long lead time and high minimum order. Also pneumatically, so the alternative would be like pneumatically actuated or like some sort of electric actuator, but those are bulky and heavy and not ideal for vehicles. So like for example, we experimented with one this year because of delays with the run valve, which Theo will touch on. And so like as a quick case study, that was a little under 5 inches longer and a little less than 3 pounds heavier than our custom solution. So for a vehicle, that really is like a significant penalty and justifies a lot of the pain that we went through to get these custom valves ready to go. So I'll dive into the poppet valves. These are the two control valves I talked about. So the fill valve and the vent valve. So I'll dig into those real quick. So these are normally open valves. So they have a spring that holds the poppet down and allows for flow from the LOX umbilical into the LOX tank. And then it also has a pilot line on the bottom. So can I pick this up? Yeah. So then when we want to actuate the valve, we flow pressure in from the bottom. It pushes this poppet up, seals with the PTFE element here, and provides a leak-tight seal from the LOX inside the tank so that when we disconnect the umbilical, we don't drain the tank prematurely. And then if we remove the pressure at the bottom, the spring will push the poppet back down and we'll start draining through our umbilical fitting, which is our drain mode, or abort mode for our LOX system. Vent valve, very similar design, but it has different force balance. This was because this was more of a last-minute component, so this was something that we had to do because we were initially expecting to have the vent valve sponsored, but when that didn't happen, we decided to create our own using leftover parts that we had from our fill valve. So this had a much higher flow rate requirement, so this has, I'll touch on that in the flow sizing section, but it was flowing significantly more gas because it's for GOX venting. So to get an idea of like the kind of forces at play here, these had an equivalent orifice size of 0.25 and 0.354 respectively, and they had pretty similar like spring force coefficients. but they had significantly different sealing forces, and that's because of that difference in effective area. So when we look at the, or we can go back one. Okay. So like this area here is significantly larger than if we went back to the fill valve. Can you go back one more? This has a much smaller area, and this created some issues for us. But this was required because of the larger flow area that we needed, whereas we could get away with a much smaller orifice on our LOX fill system. So, so kind of walking through this, basically the way we address that is we put a flow restrictor on the vent valve going to our dome loader regulator, and this prevented the tank from being pressurized before the vent valve could close. So a failure mode we're running into is that the tank would pressurize to 700 psi too quickly, and then the valve would not have time to fully seal. And then at that point, there wasn't enough of a difference in pressure for it to fully engage the PTFE. So it had pretty significant hysteresis. So to address that, we put a 10 thou flow restrictor here. Another issue we ran into is that the surface on the outside of the poppets was exposed to ambient air, and that ended up freezing over. So really, it kind of created like a system-wide limitation of we couldn't recycle without like fully warming up again and evaporating any frost buildup. So that's definitely something that we can look at improving in the future, but for now it's kind of a constraint that's imposed by the valve design. We can only do like a single cycle before we have to wait an hour or more for the system to warm up and the frost to evaporate. Yeah, and then component validation. So fortunately, these components worked pretty easily off the bat. So we didn't have to do a significant amount of iteration after the hydroside testing campaign, except for the issue that I identified. But in this case, we said that that operational constraint was not too restrictive, and we could work around that. So we went with we kind of continued to use that valve design with the added flow restrictor that I talked about. Yeah, so now Theo will talk about the run valve, and you'll kind of dive into the specific analysis that we used for designing all of our LOX valves.
Okay, so to overview, the run valve is the connection between the oxygen tank and the injector. So at T minus 0, the run pilot solenoid will open, and that piloted line will come to the run valve through here, and then push a piston up, which will actuate it, and the LOX will flow into the injector. Shit, my bad. Thank you. After that brief intermission. Okay, and then that's the overview of the run valve. For materials, and this applies to all of our valves, we use passivated 303 stainless steel. 303 is much more machinable than 304 and 316, which are more of an industry standard. And for our purposes, where we have many parts overlapping, we need good tolerances, so the machinability was worth it, and it has a similar oxygen resistance to 304. For all of our sealing, we use PTFE. PTFE is very inert and performs well at cryogenic temperatures. So all of our both dynamic and static seals were PTFE. This is the operating principle of the run valve, and it's similar for the other two valves, where in its closed state, the spring is pushing the piston down. It's sealing against this PTFE seat at the bottom, the one in pink, and that's preventing LOX from entering the injector. During actuation, the pilot solenoid will open, high pressure gaseous nitrogen will flow into that cavity, and it'll push the piston up with about 1,000 pounds of force. That will overcome the force balance of the spring and the LOX pushing down on the piston from the top. The piston will open, and the LOX will be able to flow down and into the injector. And this actuation is very fast because the pneumatic actuation gives us a lot of force. Some more overview of the design. The sealing itself, this was a validated method from last year's valve, where you have a PTFE base and then a metal piston, and then the knife edge at the piston here will dig into the PTFE and create an effective seal. And that worked well on this year's valve too. And as mentioned before, the dynamic spring-assisted seals, they are extremely difficult to work with, but they do work. So everything else in the design kind of needs to work around it and allow them to function. So you'll notice that on all three of the spring-assisted seals, there's a flange because they're not flexible, so you can't like kind of squeeze them in. You need to put them between a flange. And for every flange, you don't want ice to get in, so we also put an O-ring there. So that's why you just get, it's a buildup of seals. So for simulation, we did computational fluid dynamics with a constraint of 2.5 kilograms per second of LOX flowing through, and we found that there was a minimal pressure drop about 1 to 2 psi, mainly through the kind of constricting area here, and a maximum velocity about 6 meters a second, which is good. You don't want the LOX to be too fast because high velocity LOX, if there's any FOD or anything, it could be dangerous. So you want to keep velocity as low as possible. For manufacturing, we machined all of our valve components in-house. And as mentioned before, the spring-assisted seals require very tight tolerances. This was difficult to maintain because as over multiple body pieces, you want concentricity especially to be good, so the piston can slide easily without any friction or without interfering. And yeah, but the 303 stainless steel also helped with that. It allowed easier machining, so we could focus on tolerances. For testing, we had a pretty extensive testing campaign. We started with hydrostatic testing. This is just to make sure our seals work at ambient and there's no burst, so they can structurally handle the pressure. Those were pretty successful. We didn't have any major issues, and we moved on to cryogenic testing with cold flows. These were far more difficult. We needed the entire integrated fluid system. We had many tests, and eventually we got it functional, and then we did a static fire, as you can see. The initial cold flow attempts had significant leakage from the run valve, so as soon as we started filling with LN2, it would start leaking out the bottom. And this was obviously a problem. You can't have LOX coming into the chamber. So for troubleshooting, we found that in hindsight, this is something that could have been caught earlier, but it was that in the run valve, the geometry of the PTFE seal was such that when it contracts, because PTFE contracts about 7 times more than the steel. So under the temperatures that we're working with, the PTFE will contract and it'll just leave a gap between the piston and the PTFE. And the LOX was, or the LN2 was literally just dumping through that gap. There is a spring on top of the piston pushing the piston down. But the crucial thing here is that the force balance needs to be not only negative when you install it, but it needs to be continuously negative throughout fill. Because if the friction is too great and the piston will simply stay in place and this gap will continue to exist and the seal will fail. And that's what happened when we first tried it. This is also why the other 2 valves we made that Adam touched upon, those seals didn't fail in the same way because the geometry meant that when it contracts, it actually contracts inwards and it improves the sealing. So to look at the force balance a little bit more, we have the force of the spring, the force of the pressure in this region, and because the temperature is dropping, we also have a little bit of a vacuum forming in the spring cavity, which also has an impact. So like I said before, in order to seal successfully, the net force needs to be negative during cryofill. And this implies that the static friction needs to be less than 31 pounds in order to maintain contact and seal. So we analytically found approximate values for the friction of these spring-assisted seals. And low pressure testing also revealed it was about 20 pounds of friction, which should be enough to seal. So the mystery was that when temperatures got so low, there was an additional, it turned out to be about 70 pounds of friction. And this was very difficult to characterize because it's not easy to just go in your backyard and do cryogenic testing. So from our perspective, the piston simply wouldn't move. And it would be impossible, this 90 pounds number, we had no idea how big it was. We had no idea if it was 5 pounds or 50 pounds or like it could be some other interference caused by cryogenic operation. In the end, our leading theory is that the thermal contraction of the spring-assisted rod seals was inducing thermal stress in the PTFE, which was then kind of squeezing the piston, and then that normal force was increasing the friction significantly. The ultimate fix, you'll note this is like an older design. This was the first design that we manufactured. And then after all the changes, it looks like this. And the most obvious difference is the massive spring. This spring is about 4 to 5 times more powerful in this state. And that basically pushes past all the other aspects of the force balance and just slams down on the PTFE to make sure that we seal no matter what's happening, no matter the friction. And this worked perfectly ever since we implemented this change. There's been no leakage through this bottom seal whatsoever. And it actuated successfully several times. For future development, you want to talk about this? Or?
Okay, so we didn't have any sensor data on our injector to quantify the valve pressure drop, so that's purely theoretical, though we're quite confident that it was less than 1 to 2 psi based on our experience with previous testing for these style valves. We also want to build valves with more environmental resilience to just icing and frost buildup, so that we don't have to worry about like for example, we can fill multiple times and still be at cryo, rather than being limited to one full cycle. And we also want to improve our spring load seals, so see less reverse leakage, because that was kind of a persistent issue. So that's probably a combination of our machining and just overall tolerancing and inspections to make sure that the parts are dimensionally accurate and also accurate in assembly to one another. Yeah. So thank you so much, and best of luck at launch.
Alrighty then. If you have any questions, make sure to talk to the Columbia folks about valves. Woo! We love valves in this society. Okay, so our final podium presentation is from our friends over at Put Rocket Lab, who will be doing a presentation on their propulsion system of their Hexa rocket. So whoever's coming up to present that, please come up to present that. Folks. And again, reminder that you have 20 minutes.
Okay.
And then time for questions.
So? Można. So, hello everyone. My name is Aleksander Bożymowski, and this is my friend Jakub Tomiak. We are a crew member of a student association called Put Rocket Lab, as you see, and we are from Poznań University of Technology, which is placed in Poland. And today we are going to talk about our Hexa rocket propulsion system. More specifically, we will tell you about our GC feeding box, swivel injector, fuel grain manufacturing, our hybrid rocket broomstick plus 2 plus, and about you will see our full flying full flow plot. So, first of all, I would like to talk about our PCC, which means Portable Command Center. It is a mission control unit which allows us to control and monitor all of our subsystems on the land side, which includes
LPB, which stands for Launchpad Box, Relay Board, avionics, and GC feeding box. As you can see, it is a profile mission. We can see on our PCC. There are, sorry. You can see we have a hydraulic schematic of all the system and the rockets. We have a live view of all of the values in pressure transducers. You can see the pressure in, the pressure in tanks, and pressure inside the Hexa rocket tank. You also can see voltage meters and voltage readings, temperature of avionics, and status of trackers in our avionic bay. Now you can see a GC hydraulic scheme, which, as you can see, have two inlets, which connects via to multiport via two valve valves. It has a pressure transducer and pressure gauge. Then you can see we have a heat exchanger, because we are doing something like we have a really high pressure inside the tanks, and then we, with heat exchanger, we exchange heat from one medium to another to reduce the density and the pressure of the nitrous oxide, which allow us to have a really high pressure before the heat exchanger, and is allowing us to reduce the speed of filling the tank. You can see two filters. They have been made by our team to reduce possibility to have any particles or debris in the system, because we develop our own SRAT electronic actuated valve, which is placed here. And it has a PTFE seal, so we don't want any debris in there. We also have our CO2 line, which allows us to pressurize the system and check for any leaks, and check the pressure inside the tank. You can see also the emergency release outputs, which anything occurs while tanking. We can depressurize the system using 3 valves, which one is normally closed valve with a canal of 6 millimeters, which allows us to drop really high pressure in quick time. There's a second one, normally open solenoid valve, which is logically implemented to if we have a power loss, it automatically will open and depressurize the system. And the third one is hand actuated valve with a line attached to it, so from the safe distance we can depressurize the system. I want to talk about our ground support equipment evolution, because they have been made a lot of new the main problem with the older version was we have a straight connection, and when you want to tighten the one end, you actually loosen the second one. It was very stiffened. And we have a lot of problems with leakage. We have been using solenoid valves which were parallel, and they have problems with seals while operating. So we were not able to know if they were going to open and close properly. And they have like 1 millimeter diameter in the flow, in the canal flow. So it was way smaller, because in the newer version you can see this valve here. It's SRAT electronic actuated valves, which is actuated by servo mechanism, and it's connected by 3 linkages, which allows us to have smaller torque to open this valve and close. It is way more reliable, sorry, and it ensures us to that we will close and open the system. And it's also have like a canal diameter of 6 millimeters, so the flow area is 18 times higher, which allows us to tank our system, to reduce the time of the tanking procedure to around 4 minutes. Then you can see, because we have developed our own multiports, you can see these cubics which are aluminum multiports which have been made by our team and then galvanized to ensure that no threads will have a problem. And you can see the heat exchanger, which is it's Scott's heat exchanger, but it has plates to increase the strength of it. And we have one medium, which is actually a water with ice, coming inside of the heat exchanger from this side, because it's counterflow heat exchanger. And when we start the tanking procedure, it exchanges heat from the nitrous oxide. Then you can see multiport, which is responsible for any emergency release system. This is the solenoid valve I was talking about, and this is the same as main feeding valve. The main difference we have made is to make it simple, easy to operate, more reliable, and we use flexible hoses to ensure that there are no weird forces included when we tighten something. And we wanted to make it on the same level, as you can see, because this was way more compact. But when you want to tighten something, it has no room to play. But this one is way bigger, so you have this place. And we are using gauges and pressure transducers to know if the flow is flowing to the tank. And that's going to be it. And Tomek will tell you something more about propulsion.
Okay, so hello, I'm Kuba, just as Alex said, and I will take over the presentation from now on. And the final part of our ground support equipment is the feeding connector, an umbilical connector that is responsible for attaching to the rocket. And one rather unusual thing about it is that most teams, when they do something like this, they have a separate system responsible for plugging it out, and it usually fails. Now here there's nothing really fancy about it, and the only way to unplug it is when the rocket leaves the rail. It just snaps out like that. And another purpose of it is that, as you can see, it's connected to the rocket via nylon bolts, which get shared when the rocket lifts off, and this allows us to transfer its weight directly onto the load cell here, and that is one very reliable way of measuring how much oxidizer we have in the tank, and that's a technology we are very proud of. Basically, this part here has a sort of a check valve in it, and it automatically seals when the connector leaves. And with that, I think it's now time to talk about the engine itself. It's a hybrid model with liquid oxidizer, and this purpose is served by nitrous oxide. And there's a solid filigrane in the chamber. As you can see here, it's mainly comprised of paraffin wax with some additives, some of them used for performance, while others for manufacturability and ease of casting. But we will get to that a bit later on. Now you can see the three-quarter view of our combustion chamber. Here it's the filigrane. It's separated from the aluminum casing via ablative liners made of polyphenolic composites to keep it from melting away, because we want all the momentum to go this way, not all the other way, and that really helps. Most of it is protected by ablative liner, but here in the throat area where highest heat fluxes are expected, it is instead that we use a graphite insert. Pretty common technique, it's reliable, easy, and it has never failed us. Another characteristic things about it, you can see both pre- and post-combustor regions, which are used for increasing the combustion efficiency, because here the oxidation flow are not quite yet burning. It's used for them to mix very well, and this way they can burn better. Then it flows through the port and goes into the post-combustor, where it simply gives additional time for the mixture to burn thoroughly, which again increases the combustion efficiency. Here we can look at our open type injector, which we'll talk about a bit later on in more detail. And I think we can go on with the next slide. Now the fuel itself, it's as I've already mentioned, it's made out of paraffin wax with additives. It's gravity cast in special forms with a membrane inside. We use an autoclave to cure it because we want the temperature gradient to be just right. The whole process takes about 30 hours, which is long, but such slow cooling is needed to ensure that there are no cracks inside. And some of them you can see here. That's an example. That's a photo from a CT scanner, because that is also one crucial element of processing, is that we have to check if it's a nice monolith or if there are any cracks. Like this fuel right here would be pretty much disqualified from anything. It would go to trash, or if we would try to recast it. By the way, the fuel is not cast into its final form. Here you can see what we take out of the casting, and then it has to be processed in a lathe by our great machinists. That's the final product. You can see grooves for oiling seals. We use a lot of oilings in the combustion chamber to prevent any sort of leaks. And one very dangerous failure mode, so to speak, would be the hot gases going from the pre-combustor around the fuel back to the post-combustor, because we do not glue the grain to the liner in any way. It's held down in place purely mechanically. And if any hot gas were to flow this way, this would probably lead to a catastrophic failure. The fuel would probably crack and maybe even plug the throat, resulting in an explosion. But that's pretty much it, I believe. We can go on. Now, the injector itself, something we're pretty proud of, is, as I said, it's a swirl injector where the holes through which oxidizer enters it are offset from its axis in a way that forces it to go in a spiral, which ensures much better mixing, because instead of going directly through the port, all the nitrous is spread in a cone, which helps to atomize all the droplets. This ensures better mixing. Also, instead of injecting into the port where it has nothing to react with, it's injected onto the face of the grain, and it stays for a long time in the pre-combustor, creating recirculation regions of very hot gases. No, not that. Okay. And this has proven to substantially increase the combustion efficiency, because along the way we have made a lot of, basically it took a lot of development effort to come up with this, and that's why we stick to this technology even in our liquid engines, which we are currently developing along the way. We still use swirl type injectors. It's a proven technology for us. We know how to use it. And it's not just us. I thought the presentation went away, but it's still here with us. Thanks God. Anyway, it's not just us that appreciate this this method. Also, it's pretty well known in the industry. Like SpaceX uses it, and this proves that we probably made the right choice. What you can see here is, I forgot to mention that this is results from numerical analysis. In particular, you can see temperature fields in here, which further proves my point that you have, like in this case, where there is no swirl introduced, just the oxidizer flowing straight through the pod, you can see that most of it isn't even burning or doing anything, while here the field of temperature is much more evenly distributed, and this really helps with proper combustion. Okay, this is yet again a three-quarter view, but this time with a real insert, which is burned through during the static test. And one thing I want to point out is, you can see here in the liner, there's a region of very high ablation, and that's exactly in the pre-combustor where all this affirmation and recirculation happens. So that's why our thermal protection system is this thick really. It probably could be thinner, but it's very hard to measure, and so we just decided to stay on the safe side. Now, typically for the hybrids, you don't really burn all the fuel, there's some left. It is what it is. Here you can see another cool feature, that is the liner pressurization system, because the liner doesn't actually, since it is not cast inside of the combustion chamber, it will never adhere to it perfectly. So there is a little space between it and between the aluminum tube. And because of this, when you have pressure in the combustion chamber, this could cause it to crack. So to prevent it, there are a few holes in the liner, and then it is wrapped in glass fiber cloth, which acts as sort of a heat exchanger. So basically the amount of gas that enters here is negligible, so it doesn't really burn anything up, but it's just enough to pressurize the other side so that the liner itself is not bearing any significant loads. It's just the aluminum tube, and that's its main purpose. That's what's good at it, and that's an important piece of this hardware. And here we can see problem, because when designing hybrid propulsion or any other propulsion for that matter, it's important to have very good simulation tools to make good decisions. And it just so happens that we have a pretty much an Excel spreadsheet which was written precisely to simulate self-pressurized nitrous hybrid engines. And as you can see, here's the comparison of data from the spreadsheet with data from our last full-time full flow test. And it's visible that they agree very well, which further assures us that it is a good tool, and we have always relied on it, and it has pretty much never failed us. And also, this is, I think, a good place to bring up some numbers about broomstick to plus. As you can see, it can generate almost 40,000 Newton-seconds of thrust, so just at the limit of the O class. Peak thrust of almost 5 kilometers, which gives us an acceleration of around 8 to 9 Gs and over 30 meters a second of rail exit velocity, which assure a stable flight at the very beginning. Around 18 seconds of total work time, but only about 9 on liquid phase, where majority of the impulse is generated. Maximum pressure in the chamber of around 30 bar, which is roughly 600 psi, 500 psi, something about that. I'm not quite good at converting units from normal ones to weird ones, but sorry. And we hope that this year this engine will also help us reach our target apogee of 30,000 feet, and we'll see how it plays out. And that's it for today. Thank you very much for being here and listening.
Guys, do you have any questions? So thank you and see you on the launch pad.
All right, this concludes our presentations for now. We've got another 15, 20 minutes, and then we'll have the test engineering panel. That's going to be with folks from Blue Origin, from Impulse, and from VAST, I believe. So that will be quite fun, and then that will be our last event for the day. We'll take a photo, and then we'll give you guys a much needed break. So we'll be back in 15 minutes or so. All right, the tour will the test engineer panel will start in 10 minutes. It turns out that a bunch of people who are speaking on that panel, as in 2 of them, are on are driving back right now. So 10 more minutes. I don't have any particular entertainment for you right now other than watching people throw frisbees. Absolutely not. Karaoke is not on the table unless you're very brave. All right, okay. I think we have everybody now. So if you could please head this way for our final talk of the day of a little test engineer panel with some very cool folks. If you could sit on one side.
Yeah.
Take any seat. Yes. You can take any seats. Hello, everybody. Thank you for humoring me. Hey. Okay, Anna. What? Hi, Julia. So generally, like 6 minutes general time, I'll probably do like folks will have questions inevitably. I'm fairly certain that this is how it goes. There's overzealous people who will ask you questions. Try not to like general things, like try not to say anything that you probably shouldn't say to a competitor, you know, just as a general rule. But I think the questions are pretty good at guiding and keeping it, you know, focused on the general. So, interesting on that. Okay, yeah. Ask her all of the questions very, very quickly. Grill her, rapid fire. One second.
What's your favorite color?
I don't even know. This is gonna go well. Do you need a shirt?
Do you want me to shirt?
I can take the shirt. Oh, no.
Oh, I would love it.
Oh.
Yeah. I love the shirt.
Okay, and
I just
then
need a chance to
it'll be this mic passed around.
Okay.
So, okay, and you can introduce it and all that kind of stuff.
Okay. All right, I'll just wait to a little bit.
Return it off. It's just, just hold it off.
All right. Well, this is actually my first time using a microphone, so please bear with me. But hi everyone. Just as everyone's getting seated, thought I'd give an intro on what we're sort of doing here. Just welcome everyone to our conversation today. My name is Michael. I'm part of the volunteers at Far Out, and it's nice to meet everyone. And it's my pleasure to welcome onto this panel, we have George Herrera. In no particular order, we have Anna Tombazzi and Julia, I'm so sorry, I'm going to butcher your last name, Viborni. I'm going to go through a few intros, but thank you guys so much for participating and making this event what it is. George, so after previously leading the fluid system team at UCR's Highlander space program, George joins us as a test engineer from Blue Origin, validating different components for New Glenn and Blue Moon, and previously had also worked on validating the Blue Origin's BE4 engine. Similarly, having previously worked on, Anna, which student organization were you a part of? So sorry.
Oh, Acronauts Rocket Design Team. I helped on the team.
She was on Acronauts, and Anna joins us as a lead hypersonics test engineer and head of strategic projects at Cadmium. Over the course of her career, she has served in multiple design and test engineering roles at companies such as Goodyear, the Spaceship Company, Strata Launch, and more. And Julia comes to us from Impulse Space, where she serves as the Senior Manager of Propulsion Engineering. Over the course of her extensive 10-plus career, she has held multiple roles overseeing the development of propulsion systems at Impulse and previously at SpaceX. Thank you guys so much for joining me today. Great. Just to... Okay, just on a high level, hoping to start this off as we'll do some general questions, we'll do some test engineering specific questions, and then open it up for Q&A maybe in the last like 20 minutes or so. So starting off broadly, like what initially drew you to test engineering in aerospace and what has kept you in the field? I feel like you guys all have such great stories, and maybe we'll just go start at Anna and then we'll pass it down.
Oh boy, okay, sensitive microphone. So I helped found the rocket design team at my college, which was in Akron, Ohio, and we started at a competition much like this. There's about 13 teams in New Mexico, and the environment was awesome. Learning to work with the team was awesome. Having tight deadlines that you absolutely need to meet, and coordinating that with your fellow teammates. I mean, the whole test environment, what you're learning right now is actually really applicable to real life, especially in the test field. Those last minute problems that come up that you have to figure out or else you're not going to fly. It's kind of like a love-hate relationship. It's super fun and really not fun when you can't make it happen. So yeah, I was lucky to come out here and work for Virgin Galactic when it was the Spaceship Company and start off as a propulsion test engineer. It was super fun. Kind of just rolled down that career path ever since.
All right, so I got into, when I was at USC, I was actually thinking I was going to go into like jet engines, and then SpaceX, because of proximity, invited a student group to tour their facility, and I remember specifically like walking in that place and how glamorous and high tech and like very enticing it was, and I was like, man, this is where I've got to be. So that's what drew me at least into SpaceX and propulsion. And what's kept me here and really kind of guided my career towards test engineering, even though I am in propulsion, but that goes so hand in hand. You really can't predict what a propulsion system's going to do with analysis tools. Kind of the only way you learn if it works or not is via testing it. That's where the rubber hits the road, and it's very exciting. I don't know if you realize that. When things are blowing up, and yeah, like you were saying, Anna, like the day of, there's new issues that pop up, and it's like constant troubleshooting and problem solving. It's really exciting and kind of addictive, and it's kept me involved my whole career.
Hello. So what drew me in test engineering? Me personally, I can't be sitting at a desk for too long. I have to be outside, moving around, getting my hands dirty. And I think a lot of you guys can relate to that as well. You guys are out here in the middle of the desert, getting your rockets up there in the sky. That's fantastic work. And that for me is like what I want to do the rest of my life, up until I get like arthritis or I have to sit at the desk for this. But the work you guys are doing here, I've seen all you guys' projects. You guys are doing absolutely fantastic. This is exactly what industry likes to see.
Cool, awesome. Thanks you guys so much. I don't think you're going to get arthritis anytime soon, George. You know, it might be many years away. But maybe as like a good segue, I think test engineering oftentimes is kind of a big umbrella, and it means a lot of things at different companies. Just for, I guess, everyone's visualization in their own minds, like what does a typical day-to-day look like for you guys? Like where are your efforts mostly focused in the test pipeline, I suppose? I guess we're going to stick with the shuttle back and forth.
All right. I'm sorry, guys. I would say, a typical day is, let's say, you're out, you're prepping for like a hot fire or something, testing out some new systems. You get there early. Hopefully someone brings some donuts. Not kidding. Only come for the donuts. No, but you're getting the system set out, so you're doing initial checkouts, making sure you have continuity between the site and wherever you're operating out of, sea containers, things with outside of your blast radius, checking your systems, probably checking pressures. You probably preloaded your tanks the day before or something. You're checking temperatures, making sure that the system's looking good to be on condition. And then you're going to go through a very, very long series of basically a procedure, right, where you're coordinating and talking to all of your team, making sure that you have really clear communication. So you follow all the steps in the procedure to set up your system. And then you have your T-minus 10 seconds or whatnot when you actually have a hot fire or something like that. And then immediately afterwards, you probably have lunch and speed back to wherever your headquarters is to give a debrief to the rest of the folks that are hanging back there. So everyone's rooting for you, but sometimes things come up and you don't leave till 7 or 8 at night because you're still trying to find issues and finally perform the test.
Similar, yeah. Days generally start with checkouts. I call them also walk down. So as a responsible engineer, show up to the hardware and making sure that everything's in its intended configuration. Oftentimes, like we might have a to-do list for technicians to replace a check valve or a pressure sensor, and before I can give my buy-off that we're ready to go into test, I need to verify that those things are configured correctly. So it might be like on an instrumentation swap, you would do end-to-end to verify functionality. On a check valve, like ensuring that like the direction is correct. Many times those get swapped or misconfigured, and then you've cleared, you've chilled in, and then at the you're getting ready to test, and then you're like, oh man, we don't have any purge yet because that check valve wasn't verified. So yeah, just going down a list and making sure that you're in the right configuration to proceed into test, getting into procedure, and hopefully at that point you've prepared enough that you're not flying by the seat of your pants when you're actually in a test operation. Like things should go smoothly at that point. Yeah.
So I've been on both the engine side of the testing, and it's very similar to what Julia and Anna have described. And also I've done the component level testing for New Glenn. And that day-to-day depends on whose article we are testing. So maybe it's a tank, or maybe it's a pump, maybe it's a valve. It really depends who's coming in. But we'll start our day with a morning meeting with our technicians. We'll talk to them, see what needs to get done. Maybe something broke last night, we need to fix it. We'll talk to them, get the facility sorted. Then we might replenish our commodities, so any fuel or oxides we're using, we will top it off, make sure we have enough for tests. Then we'll start configuring our facility to start routing our propellant to wherever the article is, and then we'll perform the test. And that test looks basically, we're in a control room, we follow a checklist, step by step, we do some verifications, we do leak checks, we do everything to make sure the facility is absolutely safe before we introduce any sort of commodity, and then perform the actual test.
So for Anna and George, like, who's your donut person? Who provides the donuts and keeps you guys happy? Do you guys have one, or?
It's usually someone who loses a bet.
Oh, that's the worst.
Yeah.
So at my test stand, we have a rule where whoever is late has to bring in burritos. So we just hope someone comes in late that day and we get a bunch of burritos. Also at our site, since we're in the middle of nowhere, Blue Origin is kind enough to provide us food and snacks that we can have during tests. Yep.
All right. Into the, sort of the meat and potatoes, over the course of you guys' career, like, I'm just wondering, what are some of like the hardest test campaigns you guys have been a part of? The ones that really have like pushed you guys, have to find new solutions, the ones maybe you agonized over for a long time, but eventually finish QTP or ATP and you're like, oh great, or like def testing and you feel really good about it. Kind of like a white whale maybe.
Yeah, I mean, there's been a lot of smaller test campaigns, like Julia mentioned, with like valves, checkouts, conditioning, making sure that things will perform in a vacuum or under cryo. I wouldn't say it's like super satisfying when you have a valve that works. You're just like, oh, thank God I can buy from the supplier again, and I don't have to find another one that has a long lead time. But I would say, much like with you guys, when you launch your rocket, there's nothing that comes close to like that finale of like countdown and like crossing your fingers, like hoping it's going to work, hoping that everyone crossed their T's, dotted their I's, and then it finally launches. So that's always super satisfying. I think every time anything I've worked on has taken flight, that's kind of really been like the moment as to like why, all the early mornings and late nights and weekends are worth it. And it really is worth it too. It's a great feeling.
So many challenging test campaigns. The one I'm thinking of was getting Raptor onto Starhopper for the first time and like making it into what you would call a rocket. Before we had just done years of like ground testing, so it's kind of like when an engine becomes an adult and it has to like interface onto the stage and be operated on a stage. So a lot of new things there. New things. I mean, and granted, Starhopper was a glorified water tank. Like literally, we hired water tank welders to build the first one. So there were surprises, like the first time we mated the engine and opened the pre-valve, like a ton of water was in the tank, and like cigarette butts and sand and like all this stuff went straight into the engine. So like things that you wouldn't think is like high level propulsion engineering that you're having to work through. So, and I think back on that campaign and like I remember being like just so burnt out and like night after night of like 2 a.m. and testing and all that. But like when I look back and what I remember is like the success with the team, especially with the team and the people that you work through all those problems with. Like it's super bonding, and like you'll have those memories forever.
What sort of thing gets you through like long campaigns like that? Like motivates you?
Oh man, I don't give up on things, and on that one, I don't know. It's hard because like Elon's such a driving force at SpaceX. So like there was really no choice. I think what really got me through it is knowing, like on some level, I knew how good it was going to be for my own like personal development. Like I had a ton of responsibility, and it was fun working through the problems. Like just incremental successes like really are rewarding. So if you're like struggling through it, just know that a couple years down the road when you're solving some problem in your career, like you will take this stuff you're learning today with you and be a better engineer after you get through it.
Yeah, for me, it's not necessarily the most difficult thing, more of a more mentally grueling is any sort of test that's a thermal cycle and cryo. Those, and especially if it's a large volume. Cryo takes forever to chill in, and depending on which cryo it is, it might even take longer. And if you're filling up a massive tank or a massive volume of cryo, those tests take hours. And it could be as simple as just opening one valve and closing that valve at the appropriate time, but you have to be there to do it. Those are the most exhausting, in my opinion. Yeah.
Thank you guys so much. That was really insightful. I think also what I'm realizing, again, I'm a little bit new to test engineering as well. But there's a bit of like an unsungness about the job. You sort of almost are like attached at the hip to like REs and stuff like that. And when people think of a component, maybe necessarily they think of the RE who designed it or something like that. I guess just sort of like to put in the spotlight, what are some accomplishments of yours that you don't necessarily have the opportunity to speak more about, but actually you feel like deep pride and great success from? I know there's maybe a bit of a thinker that you have to think back and we can revisit it later on. Please.
So I am the one that, like, I'm the RE that maybe gets the glory, but I will sing praises for our test team. So you guys just went on a tour of our test site. A year ago, that was a concrete pad. So they've built out that entire facility, and not only just like the hardware and GSE equipment, but all the procedures, and we're figuring out how to do data for the first time, and how to safely test, how to do safety, coordinating with the airport. Just like, there's really so much to do, and we would not be successful as a company. I would not be successful in anything I've developed if it wasn't for the test engineers. Like, there's so much a part of getting to the end result with a successful test.
Yeah, little successes on my part. I think things I contribute that help improve cadence is a big one. It's really overlooked, but it really helps the team a lot. Like doing some sort of automation, or maybe making a jig to manufacture something. Just something to make everybody's lives a little bit easier goes a long way. Yep.
Yeah, I think kind of piggybacking off of Julia's response, I came from some companies that were a little more established, like Virgin Galactic. At Strata Launch, like, the RE was the person who was doing the testing, doing the quality, doing the installation of some technicians on the vehicle. Obviously, the first flight of Talon, which went hypersonic, was really, really rewarding. And then having the opportunity to build Cambium, where I am right now, from the ground up. I mean, we started over here on the airport in an old animal shelter, because that is the only building that was available on the airport. And then we didn't hire a facilities person for like 2 years, and so I was like the manager, the hypersonics person, the facilities person, like building up everything, kind of like it sounds like you did at your test site. And then when you actually like look back 2 years later and you see all your team, all the successes, going through Series A, fundraise and everything, and thinking like we did it and like we're moving ahead. It's really exciting.
Nice. I think you deserve a week at the beach after that, I think. Really. I guess one of the troubling parts, just in tests in general, is like when you get like that one intermittent, like kind of almost anomalous bit of data, and you're just like, is it real? Is it not? How do I dig down into this? What do I do? What is your guys' like personal approach when it comes to that? Do you just go, oh,
Oh man, if you've ever dealt with electronics, I'm going to say not having good ground is the worst thing that can happen. Yeah, I mean, there's definitely scenarios where you like think that you've got everything under control, and then some wiggle shows up in your diagram, right? And you're just like, what is going on? And so I think, like, first of all, like talking to people who've worked on the system before you, that's like your number one shot. Like who's familiar with like what could be going on? This is probably manifested in the past. Like what have we seen? What do we know? And then just taking a first principles approach. Like I would not recommend pulling out your textbook, but just like use your brain, and think about what's the most likely thing that can be causing this, and just start to work down from what can I check out right now? What's the easiest to look at and what makes the most sense? And there's going to be times where like, even if whatever part of your engineering brain wants to like find out the issue, sometimes it's just easier to replace a sensor in the moment. You don't have to. Sometimes the right solution isn't like the fixing it solution. Sometimes it's just moving on with your day and getting to a point where you can test.
That was a good answer. I would say maybe taking it slow to start, and I think when you're actually like troubleshooting something, that I see a lot is like people will presume that they know the answer, and they'll like kind of tell you what's wrong with it without like really understanding the scope or just not being accurate. So I like to say things like question requirements. That's kind of the mantra or the formula, whatever Elon called it, but question assumptions maybe, and like what is that person basing their judgment on, and like just making sure that you also agree with that and like where that's coming from. And then don't just chalk up a weird trace to not being physical. Like, I think as you gain more experience, you'll be able to like know what's like a real trace versus a ground or noise. But sometimes things do really weird things, and you got like your instrumentation, and you got to dig in further because it's like a warning of something pretty epically wrong. I've had that happen. Things are epically wrong, and we're like, oh, no, it's fine. It was not fine.
Yeah, so in test engineering world, we have a hierarchy of safety. I don't know if you guys have heard of it. Basically, at your top, at the top of your safety pyramid, it's going to be personnel. So people should be kept safe at all times. That's who you should be protecting at all times. Then you have your facility, and then you also have your articles. So you use that pyramid to help verify, let's say you have a pressure transducer that's reading too high. What's the consequence of that pressure transducer, and how does that affect my safety pyramid? So you go through that analysis just to see, well, what exactly goes wrong, and then continue with tests if the consequence is minimal, or abort if you think it's too much of a danger. Yep.
Awesome. Thank you guys so much. It is like a classically like head spinning thing sometimes to look at it. You're like, okay, so these give us like some good approaches to dig down into data and basically bottom some of this stuff out. Now this next one is a little bit more geared to Anna and George, who have done some like student rocketry, but Julia, for maybe this applies more towards like coursework that you had in school and some challenges on projects and the approach. But like, what are some things that you guys have noticed that's different from coursework or like rocketry teams, you know, working in college and being out in industry, you know?
You know, I was just thinking about today. I picked up a book on mechatronics, and I flipped it open, and I saw a bunch of differential equations, and I was like, wow, I haven't done Diffie-Q for a long time. I think I need to start there. School's important, specifically not like memorizing things, but like knowing how to read really deeply into a subject and like having that fundamental understanding of first principles that you can draw from, which help you solve problems in the field. That's probably the number one thing that I took away from school. But I definitely did skip a lot of class time to work on rockets, and I don't regret it. But see, the question was also differences between rocket team and how's your approach changed? How's my approach changed? I think like Julia said, slowing down a little bit. I think on rocket team we were like so eager to immediately there's a problem, we're going to start looking at the solution now, and I'm going to start jigsawing some new fins out of a piece of wood plywood like on a trailer, right? And they maybe don't have the right profile, and now the flight's messed up, and oh, I should have done that. In the real world, you kind of want to think about things a little bit more when you can. Think about why you're doing it. Is it the best way to do it? Should you actually be the person that's doing it, you know, even if maybe you want to? Yeah, just kind of like putting your ego aside, taking more responsibility, kind of adapting maybe more of a teaching mindset too, for others who maybe, you know, aren't as familiar with the field, and learning really to integrate and work together from there.
You made me think about the timeline difference in school. Everything was like either semester based or like year based, and like short term kind of thinking, where like in your career and in these projects, like they're many years out before we're going to launch, or you know, it's like many year long development test campaign. So I think just that change in perspective of like it's the turtle not the hare or something like that. You're in it for the long haul, so yeah, slowing it down and I think applying more strategy of like where we spend our effort, or you have to like coordinate with your team, your manager, stuff like that. It's a lot different, and I think the stakes are a lot higher. I think you're charting your territory at a company, generally speaking, versus like on a student group, like yeah, you have some like unique constraints with like budget, but for the most part, a lot of this has kind of been demonstrated before. So there's like an answer versus an industry. There's not an answer defined for you. You have to go find that answer out, which should be inspiring. It's fun.
So on a academic perspective, I'm a chemical engineer in an aerospace field, which is rare, what I've seen, and not natural, what I've been told. So from coursework to industry is very minimal transition other than your basic transport phenomenon. From my experience in like amateur rocketry to industry, the biggest difference I've seen is regulation. So things in place, test requirements, are a lot more flexible in amateur rocketry because you're the one designing it, so you can test it however you see fit. But in industry, 9 times out of 10, you're testing someone else's design, and they have certain requirements that they need met, and you have to, them being your customer, you have to meet them, and you have to work with those tight restrictions.
Awesome. Thank you guys so much. The shuttle system is a little bit weird, but I think it works. I think before we go into QA, want to touch on a few questions that may be very interesting to a lot of the students here, especially since they're looking to start their careers and find out their place in the world. I think one thing that's definitely like on their mind is like, well, I'm a senior in college. I've done rocketry. I've loved it a lot. Like, how do I stand out to these companies, and what can I show from my experience that would really highlight myself?
Yeah, I think the interesting thing about design teams in general, recruiting from them, is if you're recruiting and you're looking at someone who worked on a design team, you either know what it means to have been on one or you do not. And there's not really an in-between. And so finding a way to showcase your work and what you've been involved in and designed and tested throughout your 4 or 5 years in college, besides just putting a little line in your resume that says, I don't know, structures lead, rocket design team, is really important. Like, consider creating a portfolio of your projects with pictures, CAD, analysis, a little more in depth so that they can grasp what being on the team meant to you and how it really has built you as an engineer, besides just hoping that they get that out of a line or two on your resume.
I like the idea of the website. I think that does help you stand out. I do a lot of hiring, and I see a lot of candidates that have student groups on their resume, and that used to be unique, and unfortunately now less so. So I think you need to do the work on demonstrating that to people that you're trying to get to hire you. I see a lot of people show up to phone screens or interviews like not very confident in what they know or like how they're selling themselves. But what I would recommend is practicing. Like, I didn't do it enough of it when I had just recently graduated. It's very cliche. The recruiters or the career people at university would tell me to practice your elevator pitch, and like I never did, but it's like really does help you stand out of like knowing what you're going to showcase. What are you talking about? Like, what are your skills? What makes you different? Like, have practiced that, said it out loud to somebody, and I think it really will help you stand out. And then, yeah, anything you can do to go above and beyond. Having a website, like I didn't know that Charles Sharp was a big deal, but he reports to me. And I specifically looked at his website. I did know that, and I was like super impressed with what he did in his free time. So like, yes, you may be an A+ student, but like, what do you do in your free time? That's where you're an engineer, and like applying what you've learned, that's what distinguishes you.
So baseline, what y'all are doing here with Far Out is very fundamental, and employers love it. More importantly, what will make you stand out even more is ownership over a certain component on your system. Not only does ownership show that you have some sort of competence in engineering, but you now have a talking point during interviews and you can have any sort of freedom to talk about your article and show off your engineering skills to whoever's interviewing you. So having that ownership on your system is very important.
Awesome. Thank you, guys. Just a kind of a rapid fire one. If you guys had a website portfolio, did you guys have one picture that was like a little silly? Were you guys next to the rocket? Yeah? Maybe one or two? You're like, it shows off like your character a little bit. Awesome. I think another thing that might be interesting for students is, coursework is one thing. It seems like also like clubs and extracurriculars are becoming more common, right? Like apart from those two, are there any other things, maybe like personal projects that could also help me stand out? And,
I mean, this is kind of like covered in Rocket Team, but like learn to build shit. Like know how to use a drill, know how to design things that don't have crazy tolerances that machinists can't make. Like learn how to use a lathe, learn how to mill, learn how to weld. All of those things will make you a much better engineer and designer, and also save your company a lot of time and frustration. And also the technicians that you really need to be on your side won't be annoyed when you tell them to build something that's actually impossible to build.
I second that. I don't know if I'll come back to me.
I guess more on the behavioral side, showing that you're easy to work with. You'd be surprised how having a teammate on whatever job you're working at, having constant conflict with them can affect your cadence during testing. So making sure that you're able to compromise and work with a team is very important when you go out into industry.
Is there something that maybe is not covered on these questions that you feel is important to you, or something that you'd like to share just in general to audience here?
I think one important thing is kind of becoming a little more strategic in testing. A lot of times on smaller projects, like you guys might be working on now, it is easier, better, cheaper to just test it out and see what happens. But in scenarios where you're dealing with human life and your test team, just adding an extra level of diligence to, if you don't know what you're looking at or designing or talking about completely, just asking for help. No one's going to think you're dumb. You don't have anything to prove, but that part of diligence is really important to keeping everyone safe.
I have 3 things. The first one, if you haven't heard it, is test like you fly. That was a huge thing in my career to have learned, is you want to uncover the failures of your hardware, or like uncover what's wrong with your hardware on the ground, so not in space. And to do that, you got to get really creative. You got to have good analysis. You have to, work with all of your interfacing teams to understand the problem and get it right on the ground so that you uncover those things, like I said, not in flight. The second was fail early and fail often. My whole career, that's been a huge mantra, and it means that you got to be hardware rich. You got to be willing to blow it up, and that's the fastest way you'll learn, because you could spend years analyzing the problem in a computer, but it will never predict what's really going to happen, and there's truly no way to go about it faster than just getting into test. And the third thing was, people often ask me, in particular with operations, test operations, if you don't have experience, how do I prepare or train? I learned to be creative and proactive with thinking of things that will fail and playing out that scenario in my head, so that one day when it did happen, I knew exactly where to go. I think that's something that you can do without necessarily having the experience of having done the thing before, but before I, if I'm working with a new system or training somebody to open, the next step is like open the pre-valve. Before I let them open that pre-valve, I'm like, all right, something goes wrong. Like, how do you exit out of this scenario? And having them kind of think through a couple of ways out or some things that could go wrong, like really helps them be more calm in the situation. Again, not flying by the seat of your pants, but being prepared to safely get out of the situation.
I also have three things. Number one is test engineering is probably the best field any new grad could get into because you work on systems and you learn how real life works compared to design, right? Second thing is if you do go into design first, I imagine a lot of folk here will ask a test engineer when you're designing your stuff. See if they have seen something that failed to something similar you're designing. And then you can make those adjustments before you actually get into test. You can save a lot of money like that. Third is, when you're at the test stand, listen to the technicians. These people have been working their whole lives in this field, 30 plus years of experience. They will tell you something is wrong like years before it happens. They are very knowledgeable. You'd be surprised how many times our engineers will ignore our technicians' advice, and then the thing they said would happen happens.
Do you have to buy the techs a burrito if it happens? Or we get overtime. Okay, all right. I think that just about covers what we got in terms of prepared questions. I think we can open up to QA. Yeah, I don't actually know how to get this one around. I'm just gonna run it down. All right. I see a question right here. Can you say, what team you're on, what your name is, and then your question?
Yeah. Hi guys, my name is Brandon from UCR, representing Highland Aerospace program. First off, thank you so much for all the insight. It was really incredible to see how much you guys, just hearing your guys' experience as test engineers and the values and all of that stuff is just wonderful to hear. So thank you so much. My question is, I'm blanking now. My question is about, so I'm a graduating senior, and I'm starting to think about the next chapter of my life, right? This next decade, well, I'll keep it simple. So there's this one thing that's bugging me, and I'm hearing conflicting opinions from generations, is the sense of loyalty to companies. So what I see a lot in younger folk or people who are just entering industries, especially if you look on LinkedIn, it's they job hop here, and I was just wondering, what are your guys' perspective on just loyalty and I guess as a test engineer role? Is it very important that you stick it out for 5 years, or what's the kind of reality with that?
Big step. All right. Here you go.
Yeah, I mean, I think that loyalty is definitely not viewed how it used to be viewed, where, like you said, you worked at the same place for 30 years, and if you leave, it's a big X on your resume. I think that I am more cautious when I look at people who have job hopped, but as long as there's a good reason for, why maybe they left after a year or two, 2 years is kind of a good metric, because the first 6 months or even 9 months, depending on how junior you are, you really just kind of get in your lay of the land, and then from there you can start to really learn from the company. But I actually think the more companies that you've worked at, within reason, the more experience you have from a broader breadth, more companies, more different ways of doing things, different opinions, different metrics, and if you can kind of cherry pick the best of each of those companies and bring them with you for your experience, that's super valuable. So yeah, I don't really look down on someone who has had more than a few jobs.
I totally agree. I would say, let's say you're 15 years into your career and you've changed jobs every 2 years. That's 7 jobs. That can be a little bit of a red flag, because why are you needing to change so fast? And a lot of as a manager, it takes time to onboard. So I don't really want to. I've invested in you. So if you leave after 2 years, it's hurtful to the team, not to me personally. So there's that aspect, but if it's like 15 years and you've been at 3 jobs for 5 years, like that doesn't seem to be a red flag to me at all. That seems pretty normal, especially, you know, we have a lot of aerospace companies that are coming in and out of life, and people know that and feel that. Like, I don't discredit anybody for having to leave a job that's not a good fit for them. People have to move for, you know, family reasons all the time. So like, I don't think it's a red flag on your resume at all. And especially in your early career, like, I want you to find not just the place, but also the role that gets you like really excited. And I'm pretty understanding that that might take some time to find. So honor what's true to you and keep looking for it.
So I've only worked one job so far, so I can't really give you too much advice on that. But I would say go to somewhere where you're valued. You'll be a lot happier working where you are. Depending on what your own personal values are, might affect whether you job hop or stay where you are. But be in a place where your skills and your time is valued.
One thing I'm going to add, because I'm sure this is on your mind, is maybe you have a job offer and maybe you, maybe it's not your dream job per se, but like you want a job when you graduate, so you want to accept it, right? But then what if something better comes along, or, you know, what if you don't like it or something? You could definitely, I guess I'm saying this on the record, I don't care though, you can accept multiple job offers and then decline them, you know, and choose to accept the one that you really want. So employers won't really like that, but at the end of the day, like, it's your life. So don't get caught in a job that you don't want to be in if there's something better out there, just because, you know, you want to make some boss happy that you don't even work for yet. You know, it's much better to do that than to work there for 5 months and then quit because you're really not having a good time.
And that happens all the time. We get people that accept our job offers, and then the company that they're at says, actually, no, we'll pay you more. How do we keep you? And then they decline on us, and it's like, it just happens all the time. Do what's right for you. Don't worry about it. We forgive you.
Awesome. Next one. Any questions? Cool. Okay, I've got 2 here. I think Ricardo, you got second, if that's cool.
Not all of you guys have experience working at startups. My name's Jack. I'm the project manager at the University of Arizona Liquid team, and I was wondering what it's like working at a startup or not a well-established aerospace company like Lockheed or in Tucson, Raytheon, and what's that like?
Yeah. Getting my cardio in today. Here you go.
So working at a startup, you get to wear a lot of different hats. Some people like that, and some people don't. Some people want a very rigid structure where you're my boss, you tell me to do X, Y, Z, and that is what I'm working on for the next 6 months. You know, and then once I am done with my statement of work, I go and pass it on to, I don't know, George, who does analysis, right? But working for a startup is much more cradle to grave, and what that means is you have a problem, you conceptualize a solution, you design that solution, you either build it yourself or you send it out to get built, you install it, you test it, and then it gets put on the system, or, you know, maybe it fails. So if you are not stressed out about working at doing a lot of different things at once, big multitasking going on, and you really like seeing things through to the end, you'll probably enjoy startup life. Also, work-life balance sometimes can be a little more difficult, but it depends on your values. You know, sometimes it's worth it to people when you can really create something great, a part of a team. It just depends on where your priorities are and maybe where you are in your life, how important like a work-life balance is for you.
I second that. Let's see. On the topic of work-life balance, I find it interesting when people bring that one. Like, for me in my career, like, I feel like when it's brought up, it's generally with this tone that you're supposed, like, those are two different things, work and life, and like, work is my life, and I spend, 50% of my waking hours doing work. So like, of course, for me, I want it to be as exciting and awesome as possible, and like that's what I found for myself. And I would say, unless you have some sort of like circumstance, like your 20s will shape your career. If you work your butt off and just like go for it, it will pay off so much more in the end. So buck up and have some fun.
Yeah, at LSO in Texas, it's not uncommon where work is life. To put it frankly, a lot of the test engineers there are dogs, so we're working around the clock making sure we're all good. But there's a culture of we're dogs because we want to be, and we want to see an engine fire, or we want to see this article work, or we want to see something we put all our hours into to function. And then what's even better is that when we see those things on New Glenn for the first time, and it's launching, going to orbit. But keep in mind that you do have a life. Keep that balance as best as you can, unless you don't mind, working all the time.
Awesome.
Hey, I'm Ricardo. My question would be, what is one milestone you like to see accomplished with your company that you're working at, or like in the test engineering role?
Okay, one jump. All right, here we go.
Was it want to be accomplished or have accomplished?
I think want to see accomplished. Yeah.
Oh yeah, okay. What milestone do we want to see accomplished? So the company that I'm working at now, Cambium, we've developed a next generation material for hypersonics. It basically can replace titanium, and so it's been my goal for the last 3 years to get that on missiles, rockets, hypersonic vehicles, glide bodies, etc. And we are not there yet, but we've done a lot of substantial work in qualifying and testing and production for that, so I think we're really close. But that is kind of like my end target, because I know that will enable kind of like a next regime of hypersonic flight that is often so limited by weight and manufacturing challenges, and so bringing that to manufacturing out of a composite will be really exciting for the industry. So that's a big check off of my list, I guess.
Yeah, that sounds really cool. Right now we're in the heat of development, so I am responsible for Deneb engine, which is a 15,000 pound engine, LOX methane. Where you saw where we're testing the power pack, which is the pump and the pre-burner that powers it, out at our test site, and we've blown it up like 10 times. I've lost count. It's been pretty epic. So just really fighting through it. Even when I started at SpaceX, it was like things were way established there, and even I got there in like 2012. So like even 10 years in, they were so far ahead of where I'm at currently at Impulse, and just like having the perspective to be patient with that, and like it will take time. Like not only have we designed this pump from clean sheet in like the last year and a half, 2 years, we've built up the site in Mojave in that year. We've had to buy CNC machines and built up our manufacturing capability. We've built up our team and how our teams work together. So like there's just so much coming together that we're having to build. It's not necessarily as like tangible as like, oh, this power pack, but like when that gets, into a 30-second long test and we integrate it onto the engine and the engine's testing, like that's going to be a huge milestone, not just for the hardware itself, but like the entire company and team.
So for Blue in general, our main goal right now is to land on the moon with our lunar lander, and my test stand does a lot of component testing for lunar lander as well as New Glenn. So right now, that would be our biggest accomplishment. The other thing, not really an accomplishment, more like a bucket list, is I want to see something blow up that I'm working on, right? I want to get that feeling of what it's like to see an anomaly, and I have to respond to it. So, yeah.
Would you like to join our team in Mojave?
Yeah, be careful what you wish for. I've got to run, guys, but I'm going to leave you with these guys. Thanks a lot.
Thank you for coming in. Okay, I think we've got time for maybe just one more question. If anyone has any burning one. Okay, cool. And I left at the right time. Anyway, thank you so much for our panel participants. Thank you so much for taking the time and coming to talk to us. I think it's been a very insightful time. And so let's please give a round of applause. Awesome. And I'm going to hand it back to Jess. Thank you, guys.
Hello. Oi. We're back. This concludes our conference day. We would like to please, pretty please, take a little picture with everybody at the front here, which means that we will probably have to move this table. And I don't really know what we're going to do about the sound system, but it's going to stay there. I don't know the best way to do this, and I would love to have some opinions. Okay, maybe, everybody who is wearing a black shirt, go in the front here. And that means two teams, right? That's Ornos and CSI, I think. Wait a second. And UCR. So those folks will line up in the center, and then could other folks come up to the stage, and we'll try to take a picture in front of this banner. Thank you. Volunteer folks, could you kneel in front with these folks? Or sit on the ground?